Let's go. Let's go. Let's fucking go, guys. Let's actually fucking go. Yo, 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 yo. Are we hearing this, by the way? Are we hearing this? Yeah, 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 yeah. Nice, nice, nice. Hello, boys. Hello, boys. Yo, you can't see my fucking camera right now. Yep, I'm here. Yo, what's up, boys? Today is the third day of learning, learning some IT. Okay, I know. Yo, first of all, what's up? What's going on? What's going on? How was the day? Like mine's pretty shit. It's okay. Wait. Yeah, it's excellent, 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 excellent. Let me put on a tweet like real quick. Let me tweet real quick. I'm forgetting to tweet. Yo, we are fucking live, man. The fuck? We are fucking live. Yo. One momentan, please, oh. We're looking for Valorant players, Apex players, code players, streamers, content creators, editors, graphic designers, musicians. Retweet plus reply with what you are, and we will have a life-changing opportunity for you. What the fuck? What's the comment? I have a Red Gaming channel on YouTube, and you can also start a new YouTube channel for just FPS games like Warzone. Content editors, graphic designers, motion designers, esports managers. Motion designer. I'm not a fucking motion designer. I'm not a fucking editor. I'm not creator. I'm not a fucking streamer. I'm a streamer, but who the fuck cares, man? Who the fuck cares, right? We don't fucking care about the gaming, man. We don't care about it anymore, man. Void Esports. Who is this, by the way? Are they new? Yeah, they are new. Series is 2x brands powered by Dropped. Okay. What's that? New Arc Raiders updates. Fucking L, man. It's L. It's L. Dude, they do not. They like. I mean, I don't understand about these like streamers. I don't have anything like against them, but I just don't understand them. Like in anyone, like literally anyone. Oh, this is fire. This is fire. This is W update. What the fuck is a W update, man? What the actual hell, man? I'm just gonna do like this, like really quick. A review. I like Hutch was talking about that like what I liked. I'm saying what I liked. Like Hutch was telling the same thing, and Shout was telling the exact same thing, right? Like 2 weeks, 2 weeks, guys, 2 weeks. They're gonna feel shit. They're gonna feel shit. There is no actual loop in the game, guys. There is an actual loop. Okay. Let's forget about the PvP players and let's forget about the PvE players. Okay. Like forget like there's just one base. Okay, about like there's players and that's all. Okay, you have to have everyone in the loop. There is no exceptions. So, like you don't have to differentiate between PvP and PvE. Okay, you have to have everyone in the loop. Okay, because I mean, uh, like what? Like let's take an example. Take an example. Like the game is dying. Why is they saying? Because it's getting boring, man. They don't like it because like they had the expectation of that extraction shooter. They had the expectation of that, and it doesn't feel like the extraction shooter anymore, man. You just have everything every time. Like look at the fucking Symphony. He has already 14 meals, man, and the expedition requirement is 3 meal. Like what? What are we doing? What are we doing? There is no actual loop. Yeah, the loop system is like really wrong, and that's all. And that's all. Like, who cares how many guns they are going to add, man? I mean, like 1 2 weeks, okay. Even like one month, okay. Like let's take 1 month, right? No one cares. No one cares anymore. You know? Yeah, and that's really bad. Like they can't add unlimited maps, they can't add unlimited weapons. You know, that's so called. And like adding guns is just a take this. Like giving. I'm sorry for this kind of parallel, but giving a man like really small hope. Give a man really small hope. I don't know. It's kind of hard to give you like good parallel, but yeah, it's just giving you. I'm just giving you this for now, okay? And you shut up, okay? For now, I'm just gonna do my job. You just do your job, okay? And play. You know, there's 1 2 weeks, okay? They have to in 1 2 weeks, like in 1 month, or like even in 2 months. Come on, even in 2 months, come on. They have to come up with something new. Now you take this new gun, maybe new map condition, maybe. You know, yeah. No one cares, brother. No one cares, brother. Literally no one, and that's completely okay. That's completely okay. Being family friendly. It's not who I am. I'm done being family friendly. It's not who I am. What? Okay. This is a joke, by the way. I am live on YouTube. I search G on all socials. By the way, by the way, uh, yeah, YouTube, search G on all socials. By the way, what? By the way, what? By the way, what? By the way, what? By the way, nothing. By the way, nothing. Okay. G, 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 G. Yeah. I don't know. I mean, do I have to give them? I was talking about it on Twitch when I like went live. I talked about it on Twitch. Um, do I have to like give it a new video for that? Like, I'm not streaming games anymore. I'm streaming like what really I want to do. I mean, I have like there is no other working out, guys. There's no other working out. I'm grown as man. I have to work. Okay, and I'm working, right? And I can't be coming I can't be like being exhausted from work, then like streaming for 6 hours minimum a day, then making videos about it, man. I can't. And when actually like this, like it's not exciting. It's not exciting at all, you know. And I think that I have to like choose. I'm choosing the diet. I chose the direction and I'm going with it, man. I don't care. I don't care. You know. I want to be a streamer. I didn't know what to stream, and I decided I'll stream like what I'm really actually doing, you know, and that's all. Well, what? If I'm not posting the links, like no one's getting, it's not getting an attention. Taxi D Legend. There's 67 of missing Hamlins. What the fuck? Where is that guy?
I don't.
I mean, they're stream
I don't care anymore. Taxi, if I saw you in real life, I'm doing.
Oh, such COD timing. Hamlin's ghost.
Anymore. Taxi, if I saw you in real life, I'm doing.
Oh, such COD timing. Hamlin's ghost to throw a leap repulse and he just fucking gets show stopped.
I don't care anymore. Taxi. I don't.
I mean, they're stream timing.
I don't care. I'm tired of hiding who I really am, bro.
Yeah, no delay.
The fuck?
I do not have a delay.
Like, I just couldn't hold it anymore. It is what it is, big fella. It is what it is.
Golden can't make a survivor. Yeah. They're funny, man. They're funny. Miss you, Hams.
Oh my god! I did it! Lock it in, boys. Lock it in. Lock it in.
Oh my god, it's Summit. Oh no, it's all over.
Are you seeing that? He didn't miss a single shot! Summit no longer gets to play sniper. That's not allowed.
Right there.
Yeah. Maybe. Maybe. They, they have to, like, the leveling system in Arcade shouldn't be that easy. I think it's like it's much too easy, Now leveling system is easy. Um, Game plan media is who? Why does it seem that they are like from Marathon? Fuck off, man. Yeah. They have to some developments, man. Like the Raider needs like much more has to have like much more development. Like for example, like free loadout, like the Marathon has with the Rook. You learn some skills and free loadout gets like better. I mean that's what it is, man. You don't have shit. Like you go free loadout, when you don't have shit, man. Like with Rook, let's take for example. You go in, you are like you go out and you are done with like your like 3 4 8, you are done. If you go with a like free kit, man, you're not doing shit. You're probably dying. That's why. Like holy shit. New arc, new that, new this, no one fucking cares. No one fucking cares. Yeah. Reposted it. Today we're gonna find the computer architecture, guys. It is, let me tell you, hour and a half course. It's part of Foundations of Computing Path. And we are gonna be learning that. Okay, we're gonna be learning that. Also, there is a peripheral device included in this as well. It's a volumetric to keep your brain off the computer memory. Yeah, it's included. Then in this path, there's actually like many useful things. I think that I'm gonna be doing this path uh, for operating systems, mathematics and logic, foundations of computing, data structures, yeah, algorithms, human-computer interaction, parallel and distributed computing, software engineering principles, um, implementing algorithms. It's a lab, and the guy did foundations of computing lab, working with data structures. Yeah, and I think that this is the real one. No, it's from, I don't know, like who is it from, but mm, mm, it's a path. Create just a path. This is from Ned Bellavance. Like this guy's Terraform fundamentals, infrastructure as code providers, a new content like April 2026. Season prep for Vault Associate and GitOps validation and testing, advanced HCL models. Holy shit! What the fuck? Tires things. Architecting with Google Cloud Platform infrastructure. Yep. He has some courses, but by Philip, by David, by Kevin, by Amar, by Michael, by Amber, by Robert. Algorithms data structures are from Robert Horwick. Who is that guy? From Amber, we have one thing from Simon, Philip, Ned. Yeah, who's Robert? Robert Horwick. Author, no, 1256 followers, algorithms, founders, computing data structures. Yep. Same data structures part 2. Yeah, he also has a part 2 of like algorithms data structures. Yep. String builder internals, algorithms data structures part 1. He has a part 1 and part 2. Okay. Yeah. Yep. He has like 5 hours of algorithms and data structures. So as we are guys nerds and stuff like that, we barely go out, and even if we go out, we are gonna hang out with the friends and do nothing and like play video games and stuff like that. Just be nerds. Sit on one place and don't take like physical activities. We are gonna work out right now. Okay, we are going to work out right now. Fuck yeah. Let's go. Let's go. I'm not learning backflip anymore, but I don't know why, but I'm not gonna be learning it like for now. Okay, we have to lock in, guys. Lock in, guys. Actually, lock in. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh shit. This was 20. Like, how do I advertise? Like, there are like definitely people who want to learn the things I'm learning, right? Like, how can I advertise it? Like, for example, one guy or two guys are watching me right now, and they're doing it with me. And first of all, I think that somehow I have to kind of extract this course from there. I can really do that. I can actually do that. I can actually do that. I can download that course. I can download the courses, but which is like slides and stuff like that. I can make the guy talk in the background. Uh, yeah. So another 20. You know, boy. It's 40. How is my camera isn't good at all. Guys, trust me. We are going to get big, guys. We're gonna get big. Big. We're gonna get big, guys. Not big, big, but like big. Oh, funny. Kids out there. Are we getting in shape, by the way? Our tits are going hard, I think. Three, four, five, six, seven, 40. Eventually, guys, no, I'm being quiet, but it's how it is. Eventually, guys, it's gonna get to the point that everything's gonna go like smoothly. We are going to have a direction. We're here right now because we know nothing. We know zero, right? We are in frustration. We are mixed. Okay. Let me get water. We're gonna get to the point that everything's gonna go smoothly, and that's not gonna be boring anymore. Right now, I could risk it and download these slides, send it to my email. No. Oh. Send to my email and then show it on my screen right here. But I know it's kind of risky. I don't want to get banned or stuff like that. I know policies, man. It's from my work. I have access it from like through my work. You know. So wait a minute. Let's go. Let's go, guys. Fuck yeah.
It is hard to overstate the impact computing has had on our lives and society at large over the last 100 years. You are currently watching this video on a computer that connects to other computers via a network that is managed by computers. The car you drive, your washing machine, your cell
This guy, like teaching this stuff, Ned. This guy, Ned in the cloud. Playlist, daily check-in, Terraform Tuesday, tech analysis. Tuesdays on the edge, HashiCorp Vault, best career advice ever. Professional. Okay, let's see. Home. Azure DevOps pipelines with Terraform for cloud perspectives. Teams of the link. Okay, no man. Videos. Let's search computer architecture. Remember that attack again. The 3 new 0 days. That's news of the week. Our certification from the Cradle. Okay. What's that?
With us here today, giving his best career advice ever. It is Mr. Larry Smith Jr. Welcome to the show, Larry. What's going on, brother?
Hey man, how you doing, Ned? Good to have me.
Quantum computing, sandwiches, and superconductors. Pillars of IT. Disrupting the pillars of IT. The
Consolidation of work.
we don't care that. Basics. Chaos level. What's this? Tech podcast. This guy's nice. This guy's cooking. This guy. Day to cloud show. Not in the cloud. He doesn't have the courses like. Blog, media, posts, videos, books, courses. For Pluralsight, yeah, well, that's where I might be with. Books. What book does he have? Certified Associate Preparation Guide.
Possibly even your toothbrush, all have computers in them. Hey everyone, I'm Ned Bellavance, and in this course, we're going to learn some of the foundations of computing architecture that undergird the computers that suffuse our lives. The earliest computers were massive machines taking up multiple rooms, running programs that were configured by manually changing connections on plug boards. That sounds like a pain. To run a new calculation, you had to physically rewire the computer. More generalized computing soon arrived, and programs started to be entered using magnetic tape or punch cards. With the advent,
Right now he's showing like the big things like that we are like in the past, that kind of stuff. He's just showing them, and like other than that, you can hear the voice.
the modern silicon transistor, computers rapidly scaled down in size, vastly increased their reliability, and increased their computing ability by orders of magnitude. Gordon Moore famously predicted that the number of transistors on an integrated circuit would double every 2 years. And that prediction has held so steady since it was posited in 1965, it has come to be known as Moore's Law. Since
Moore's law is over as the number of transistors on a microchip doubles approximately every 2 years, leading to exponential growth in computing power and decreased costs. Coined in 1965 by Intel co-founder Gordon Moore, this trend has Intel co-founder, this trend has driven semiconductor advancements for decades, and smartphones, AI, and modern computing through its current limitations. Key aspects of Moore's law. Okay, driving force is not a scientific law, but an empirical observation and target that drove the semiconductor industry to produce faster, smaller, and more efficient chips. Okay.
1965, we've also seen the introduction of various kinds of memory, storage formats ranging from tape to CD-ROMs to solid-state drives, and network connections that started at telephone lines that were barely capable of a few baud to Ethernet cables that can transmit 800 gigabits per.
Guys, I have read this in one book. I would strongly recommend is how would it that basic computer language. Like how was it book called? It was like really easy written, really easy language, and actually how the information is transferred over the network is closely similar like to the telephone lines, and how the telephone lines like they were invented through Morse code, like the Morse code like is as its foundation, right? And later everything was transcribed into binary. I mean, like in computer language, like that's my theory. I haven't learned that much, but my theory is that every thing like C, like these guys, percentages, and everything, like everything has its own binary definition, and the computer just knows that, you know, when he sees that there is mentioned like 10. What's 10 in binary? 10 binary. No, binary 1. Decimal binary, yeah. Yep, 2 is 10. Yeah, right. 3 is 1, 1. Yeah, just like that. Just like that, guys. Just like that. You know, and everything has its own definition, right? You know, and for example, like let's say I'm saying I want to write something like Marta has 8 apples. Like this is written in binary when computers trying to understand this. You know, it's converted to binary, goes to like binary, like on over the network. You know, and the Morse code is just tap or not tap, right? There's pauses or no pauses, right? It's that easy. It's delivered to other computers. You know, other computer is like assembling this information like from bits. You know, that's bits. That's bits. That's why it's called binary, because it consists of bits. You know, there's a bit or there's no bit. You know, and the computer then it's assembled again and then it's delivered. I think that's how it is.
And yet, 60 years
By
later,
the way, this is like from what I have deduced from that information that like from telephone lines and like what's on networks and computers. That's all.
you might be surprised to discover that despite all this change and innovation, the underpinnings of modern computing architecture have stayed relatively the same since the core principles laid down in the 1945 seminal paper, First Draft of a Report on EDVAC, written by John von Neumann, based on work by John Mauchly and J. Presper Eckert. Looking at the EDVAC, an early computer built in 1949, and this, a Raspberry Pi from 2025, you wouldn't think the two have much in common, but I assure you they do.
Okay.
They do.
Next one. The von Neumann architecture, guys. It was the introduction. Now is Neumann, von Neumann.
Neumann was a mathematician, physicist, and computer scientist working in the first half of the 20th century. His contributions to the sciences are far-ranging and extend well beyond the architecture that bears his name. But for our purposes, we are going to focus on what von Neumann suggested in that EDVAC report and how it became a standard that all modern computers follow.
Okay.
Although the von Neumann architecture bears his name, von Neumann would be the first to point out that his ideas were built on the work of others, particularly the designers of EDVAC, John Mauchly and J. Presper Eckert, and the work done by Alan Turing during and after the Second World War. The key components of the von Neumann architecture are described as a set of organs in the computer responsible for different functions. The processing unit includes both processor registers and an ALU, or arithmetic logic unit. The control unit includes both an instruction register and a program counter.
Okay, so there are organs that the computer consists of organs. Processing unit, ALU, control unit, and includes both. And
these two components form the CPU, or central processing unit.
The CPU is formed from processing unit and control unit.
Keep the CPU busy, the architecture also includes a memory unit that stores data and instructions. The memory unit is meant for short-term storage of information, and so the architecture also includes a mass storage unit for long-term persistent storage. And finally, there needs to be some kind of input and output devices to provide input to the computer and expose its output. All of these terms are theoretical in nature and do not describe the actual implementation details. And that's deliberate. Part of the reason the von Neumann architecture has persisted is that it doesn't dictate the details, merely the general shape of computing. The major advancements inherent in the von Neumann architecture are twofold. First, the architecture provided a generalized way to load any program into a computer and use a well-defined instruction set to perform operations. Previously, on systems like the Colossus or ENIAC, programs were set using external switches and plug boards. If you wanted to run a different program, the whole machine had to be reconfigured. The von Neumann architecture made use of the stored program concept, where programs were stored and loaded by the computer on demand. Running a different program
That means that when I wanted, I would load the program, you know?
was simply a matter of loading it into memory from external storage or an input device. But where to store the program? That was the second big advancement. Rather than store the program and data separately, they were instead stored together in the same memory unit, with the instruction cycle of the CPU loading, decoding, and executing the program instructions found in memory. In fact, let's dig a little deeper in the CPU and see what's included inside.
Let's go. The CPU is the brain of the computer.
Many would call the CPU the brain of the computer, but that's not entirely accurate. Your brain includes both short-term and long-term memory, and it has an I/O bus of sorts for processing input and for generating output. The CPU by itself doesn't include those things. It exists purely to execute instructions based on what is in the stack. Some of the very earliest computers were actually mechanical in nature and had moving parts. The abacus, for instance, is an example of a simple mechanical calculator. Later iterations would add mechanical complexity to help human computers add, subtract, multiply, and divide. Famous physicists like Leibniz and Pascal designed machines in the 1600s to assist with mathematical calculations, and later Charles Babbage proposed a steam-driven analytical engine that was programmable in nature, although the machine was never successfully built. A major issue with the mechanical solutions is the tendency of physical objects to degrade and fail over time. Each toggle of a switch or turn of a gear wears down its components, and processors need to toggle and turn a lot to be useful. The invention of the vacuum tube was an opportunity to use a technology that didn't have moving parts and could switch rapidly. The vacuum tubes in question were triodes with an anode,
Vacuum tubes in question with an anode.
cathode, and a control wire.
I don't understand this, guys.
Current can only flow in one direction, from the anode to the cathode, and the control wire can start and stop that flow. Such a triode can be used to create logic gates, which form the basis for computing, as we'll cover later. Vacuum tubes
Yeah, that's like more like you tap, you turn it on, turn it off, turn it on, turn it off, or just when you tap, you know, there's a switch. No, guys, you know, I'm tapping, the lights on. I'm not tapping, lights off. Tapping, lights on. You know, if I tap, 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 this means something. You know, if I, for example, tap once, this is basically 101. Okay, if I do this, this is 111. 101.
The creation of more powerful and faster computers, like ENIAC and the Colossus. But the failure rate on tubes was still relatively high.
My theory is still in place, guys. He didn't demolish it.
With a tube failing every 2 days on the ENIAC, requiring at least 15 minutes to be replaced. And the power requirements of vacuum tubes were quite substantial. The invention of the semiconductor and integrated circuit allowed
This is a processor, guys. This is a CPU.
15 minutes to be replaced. And the power requirements of vacuum tubes were quite substantial. The
invention of semiconductor and integrated circuit.
Of the semiconductor
And integrated circuit.
integrated circuit allowed processors to shrink in size while increasing reliability and speed by orders of magnitude. Like a vacuum tube, a silicon transistor has no moving parts, but its failure rate and power requirements are far lower. Since transistors could build the same types of logic gates as vacuum tubes, it was relatively simple to adapt the abstract architecture of processors to the new technology. So what's on this discrete package that makes up a CPU in a computer? First is the component that does the actual number crunching, the ALU, or the arithmetic and logic unit, which is often shown as a V, with the inputs coming in the top and the output coming out of the bottom. This is the component that performs mathematical and logical operations. It takes inputs along with an operation and produces an output along with flags to indicate different conditions. But where do those inputs come from? Well, that's the job of the control unit. This unit is responsible for interacting with memory and registers and keeping track of both current instructions and having a program counter, as well as sending decoded operations to the ALU and doing something with the flat.
What the fuck, guys? What did I tell you?
But where do those inputs come from? Well, that's the job of the control unit. This
What the CPU does.
is responsible
No.
for interacting with memory and registers and keeping track of both current instructions and having a program counter, as well as sending
But
decoded.
how? But how? Like, it knows, like, it's already built in it, you know? Like, it's already in there that if you see this, it's this.
Operations to the ALU and doing something with the flag information that comes back from that.
You know, there's like, I don't know, millions or billions like of possible actions, of possible, like, you know, this comes after this, this comes after this, you know.
ALU. The registers are the short-term memory of the CPU, where it can stash data for use by the next operation. The data and the operations are stored in memory, and it's up to the control unit to fetch the instructions and execute them.
This is an address, right? Address or no? Instruction register, instruction address register.
In fact, the cycle by which the CPU processes instructions is composed of 3 discrete operations: fetch, decode, and execute. Fetch grabs the next instruction from an address in memory. Decode figures out what the instruction type is that's going to be executed, and then the execute operation performs the actual work and increments the program counter when it's done. We'll dig into the details of this process in a separate module. The CPU clock drives the fetch, decode, and execute cycle, advancing the process with each tick. Now, where are all these instructions coming from? They're coming from memory.
Memory hierarchy and storage.
If we hearken back to our brain analogy, the memory in a computer would be the equivalent of short-term memory that we use to retain information when we're working with it. Whereas storage in a computer would be similar to our long-term memory that persists even when we're not thinking about it. The systems for memory have changed drastically over time. Some early short-term memory used sound waves trapped in a mercury-filled tube that would be looped using a receiver and an amplifier. Long-term storage could be accomplished using punch cards or magnetic tape. You can think of memory and storage as sitting in a hierarchy. Short-term memory tends to have very fast access time.
Bytes. 1 nanosecond type registers, latency.
Timescales in the nanosecond or microsecond range, but a higher cost and a lower capacity. A CPU's registers and cache might be measured in bytes or kilobytes, whereas RAM is measured in gigabytes. These are situated closest to the CPU and have very limited capacity. Persistent long-term memory has much higher capacity that's usually measured in gigabytes or the terabyte range, but also slower access times on the order of milliseconds, making it unsuitable for the CPU to use directly. A lot of what computer systems do is try to fill the memory closest to the CPU with the data.
Wait.
making it unsuitable for the CPU to use directly.
Memory hierarchy. So there's registers, there's CPU cache type memories, there's RAM, there's SSD, there's HDD. So HDD and HDD are like storage, right? Yeah, yeah. That's why it's not. Yeah.
A lot of what
computer systems do is try to fill the memory closest
computer
to the.
systems do is try to fill the memory closest to the CPU with the data it will need for its next operation. We'll discuss some of the techniques used to accomplish this in a later module.
It's kind of hard, guys. I'm not gonna lie.
A computer is not a self-contained system. It is expected to interact with external devices and also people. If you've ever encountered a system with no visible means of input or output, you know how frustrating that can be. I/O devices or input-output devices are meant to provide a reliable interface between the external world and the computer's internal world. The earliest computing systems got their inputs through the use of plug boards and switch wiring, eventually changing over to punch cards with the ENIAC. In a similar nature, output from the ENIAC was also produced through punch cards that then had to be fed into other systems to decode the contents. The process was lengthy and not very interactive. You configured the inputs, you ran the program, waited for a while, and then you got some outputs that you had to feed into another machine. The teletype systems that were used to prepare and read the punch cards were eventually connected directly to the computing systems that were produced by the likes of IBM. This simplified the programming process and shortened the feedback cycle. Eventually, oscilloscopes and later CRTs were attached to provide output in a visual format that didn't require a machine for interpretation. Think about like green screens that you may have encountered. Not all I/O devices are aimed at human interaction. For instance, it was common to write data to magnetic tape for long-term storage. And eventually, networking was added to computers to allow systems to interact directly with each other. While the form and the format of I/O devices is varied, at their core, the computer is accepting digital input or producing digital output, and it's up to the individual device to interpret that information for an analog world.
Computer buses and data communication.
We've covered many of the major components of the von Neumann architecture, including the ALU,
control unit, memory, central processing unit, memory unit,
memory, and I/O devices. But there's one more critical component that ties it all together, and that is the humble bus. Well, no, not that kind of bus, although both do carry things around. In the case of computing, a bus refers to a communication system that carries data from one component to another in and between computers. The bus refers to both the physical implementation and the communication protocol that governs the data transmission. The physical media could be copper tracings on a circuit board, could be channels etched into an integrated circuit, or physical wires running to a hard drive. Buses are how computers shuttle data around the system, and they include many different abstract types and architectures. Looking at our diagram of the CPU and its surrounding components, the most important thing is interacting with memory, and that's accomplished via 3 buses. The address bus carries the address of the memory to be accessed by the CPU. The data bus is what actually carries data to and from memory. And the control bus sends control signals between the CPU and memory and may also be used by other I/O devices that would like to access memory. Not all buses in a computer interact directly with the CPU. And in fact, many act independently.
kind of protocols, guys. I'm thinking it about like a protocols, you know. I want to show you these pictures, by the way. I want to show you these pictures, though. Let me show you guys. Yeah, it's kind of crazy, like doing it like that. Crazy. I should have received it already. So this is the picture he's showing right now. This is instruction table. Yeah, right, like that. This was the previous picture. Let me show you it as well. He broke down everything here. Yeah, like that. Fuck off. That's Japan States. What the fuck? Yeah, this was the previous one. So there's a memory. You know, the ALU does the decoding stuff. You know, it's like from here, from control units, there goes like operation. Like you have to do this kind of thing. The ALU does things and then flags. You know, I think it sends back to the control unit. Then this control unit, I think, sends it to the memory back. You know, there's this clock thing. There's this the CPU, but it consists, right? Then there's memory. Yeah. Let's go back to that image right now.
Most important thing is interacting with memory, and that's accomplished via 3 buses, to and from memory.
Mm-hmm.
And the control
and this kind of, I think, this kind of protocols between you know, address, data, and control. You know, this between them. Between the computer, you know, when the computer with different computers, there are like protocols like you know, there are like network protocols like IP and stuff like that. No, there are protocols between layers, like, you know, and these computers like communicate with each other, right? And discuss the layers, right? Like it's in the networking, it's an OCI model. We are gonna get to that as well. I think. I think so. Yeah.
sends control signals between the CPU and memory, and may also be used by other I/O devices
Yeah.
that
And
would
this
like
control may be used by other I/O devices that would like to access the memory. You know, so maybe like can my laptop access another laptop through control? I don't know.
Not all buses in a computer
I don't know.
interact directly
I think it would have encryption.
with the CPU, and in fact, many act independently and at different clock.
So let's ask ChatGPT right now. So between RAM and control unit, there is a control bus, right? Close, but not exactly like that. Between the control unit and RAM, communication doesn't happen through a dedicated control bus, but only between them. Instead, the CPU, which includes the control unit, communicates with memory using 3 system buses: data, address, and control. Yeah. It's control signals like read, write, clock, interrupts. Okay. So, is it possible that different computer, like different computer, tries to communicate through control bus to the memory, to the memory, No, not directly. A control bus is internal to a single computer, not something multiple computers share. Why not? The control bus is part of the system, but inside one motherboard. Connects CPU, okay, and RAM I/O devices. Signal like read, write, interact. Designed for communication between different computers. It's not designed for communication between different computers. Okay, what happens with different computers? TCP/IP, okay.
Then the CPU. For instance, your GPU card.
Yeah, it stays like OCI method, yeah, the model and stuff like that. Yeah, that's a between computers. Like we should not mix these ones. This is like
It
internal
might
only.
want to interact directly with memory to load and
So what?
many act independently and at
So what?
that would like to access memory. Not all buses in a computer interact directly with the CPU.
Okay.
And in fact, many act independently and at different clock speeds than the CPU. For instance, your GPU card. It might want to interact directly with memory to load and process data to render onto your screen without interrupting the CPU.
Okay.
Some modern bus architectures you've probably heard of are PCI Express and USB. That's right, the humble USB, which stands for Universal Serial Bus. That's right, bus was hiding inside the name the whole time. Buses are the bridge that combine all the other components of the von Neumann architecture into a single system that I can use to check email, record podcasts, and play Minesweeper. Thanks, John.
I know how to play Minesweeper, by the way. I know. Okay, let's go to the next one, like CPUs. CPUs,
We already
guys.
covered the essential components of the CPU architecture at a high level, but now it's time to get into the nitty-gritty and walk through an example of how a CPU might process instructions. As a reminder, the main components we're talking about here are the control unit, the arithmetic logic unit, and registers. Those comprise the CPU.
So, guys, this is let me open it. Registers, control unit, ALU. These are the components of the CPU.
Itself. The CPU also needs external components like memory and I/O devices, but we'll come back to those later.
Okay.
The CPU's job.
So imagine there is not this one or that one.
To execute instructions from a program, and each component in the CPU helps further that job. Let's build things up from the component that is responsible for orchestrating all the work, the control unit. The control unit has three main things: an instruction register, an instruction table, and an instruction address register.
Instruction register?
Instruction register.
Holy shit.
Our control fetched, and the control unit waits for the action will the CPU be performing.
No.
Register contains the current
instruction register, guys. Instruction address register, instruction table. There has to be, but there is no. It's not shown right now.
Instruction the CPU is working on. Because operations and data are stored together, the instruction register splits things into an operation code it needs to run and the data it needs to run the opcode against. The actual operation that corresponds to the opcode is held in the instruction table. It's how a control unit knows that some segment of binary data is actually intended to be an add operation.
Binary data is actually intended to be an add operation. It's binary data, guys. Data is binary. 1 0 1 0 0 1 1 1 0 0 1 1 0. That's the data.
Instruction address register indicates where the control unit should pull the next instruction from when it completes its current cycle. Depending on the operation code, the control unit may need to send information to other components or manipulate the instruction address register itself. One of the components it may need to send work to is the ALU. The arithmetic logic unit is responsible for performing basic mathematical and logical operations. In fact, the mathematical operations are a result of performing logical operations, or Boolean operations, on binary inputs. So in a way, it's all logical operations. How is that accomplished? At a fundamental level, computers only deal with binary states, on and off, 1 or 0, positive or negative.
Guys, I was right. I know I was right. I knew that, man. I was so confident in it, man.
About building a word processor or a video game system using only 2 values. Well, fortunately, a whole system of formal logic and operations was crafted by English mathematician George Boole in the 1800s. He developed binary logic, which was later incorporated into Boolean algebra, and it describes a set of basic operations on binary inputs and outputs. Let's take a look at a few of those operations. The NOT operation is one of the simplest. Whatever your input is, it returns the opposite. A 0 becomes 1 and a 1 becomes 0. The AND operation has 2 inputs and returns a 1 only if
logic operations AND. Logic operation NOT. If it's A, it returns 0. So 0, it returns A. So NOT returns opposite.
Returns the opposite. A 0 becomes 1 and a 1 becomes 0.
So NOT do that. Yeah. AND do that. Yeah. Input A, input B, output 0. If the input is A and the input is, if we have 2 inputs, if we have A and B inputs, we have 0, 0, 0. Yep. And no, there's only one with, okay.
The AND operation has 2 inputs and returns a 1 only if both inputs are also 1. All other combinations return a 0.
Why?
It's like if I say that it is raining and I have an umbrella. The statement as a whole is true if both pieces are true. And I'll be very happy that I have an umbrella for this rainstorm. If I didn't have the umbrella or it wasn't raining, then the statement as a whole would be false and I would be all wet. Like the AND operation, the OR
if it's not raining, we are not wet.
operation has 2
Or 0, 0, okay?
But it returns a 1 if either or both inputs are also 1, only returning a 0 if both inputs are 0. It's like if I say I want a taco or a burrito. The statement is true whether I want a taco, a burrito, or both. It's only false if I don't want either. And I can tell you that's extremely unlikely. Using transistors and some clever engineering, you can make logic gates that follow each of these operations. And then using ever more clever engineering, you can combine the logic gates in such a way that you can add, subtract, multiply, and divide numbers. The ALU contains these remarkable feats of engineering and exposes them through some simple inputs. The operation you want to perform and the values on which you want to perform the operation. The result is delivered as an output back, as well as some additional information for scenarios where the returned value is negative, there is an overflow condition, or the result is 0. The inputs and outputs for the ALU are tied back to the control unit. But where do the values for the inputs come from? That's where the registers and memory come into play. Registers are a type of short-term memory for the CPU, and they live in close proximity to the rest of the CPU components. The registers are of a fixed width, referring to how many bytes they can hold, and they're wired to both memory and the control unit. The control unit contains operations to read and write values between memory and can hold, and they're wired to both memory and the control unit. The control unit
contains operations.
Contains operations to read and write values between memory and the registers and submit values from the registers to the ALU. The process of retrieving information, looking up an operation, and performing the operation is known as the fetch, decode, and execute cycle.
Kinda hard, not gonna lie, kinda hard.
Performing. Our control unit is hooked into a system clock, and on every tick or cycle of the clock, the control unit executes an operation. The very first thing a control unit needs to do is fetch an instruction to run. The control unit looks at the instruction address register and retrieves the value found at the corresponding memory location and loads it into the instruction.
So
The control unit
unit looks at the instruction address register. Instruction address registers, yeah, 00000. Maybe this, yeah, there is data, okay. Address register.
At the instruction address register and retrieves the value found at the corresponding memory location and loads it into the instruction register.
Okay, loads in it.
Process
Here,
takes a single clock cycle to complete.
the fetch process takes a single clock cycle to complete.
The instruction will be a combination of an operations code, i.e. what operation will the CPU be performing, and data for that operation. Once the instruction has been loaded into the instruction register of the control unit, the decode operation takes the portion of the instruction that contains the opcode and finds the corresponding operation in the instruction table to figure out what it needs to do. This is the decode portion of the process, and it also takes a single clock cycle. With the operation decoded, the control unit executes the operation by taking the output of the decode phase and the data portion of the instruction and actually executing the operation. Some operations may take multiple cycles to complete, depending on the complexity of the operation. The very last portion of the execute phase is to increment the instruction address register so the CPU knows which instruction to fetch on the next clock cycle. Let's walk through a brief example of adding two numbers.
Okay.
In the system memory, I have a list of addresses with data stored at each address. The control unit needs some starting point to load the first instruction, and for our purposes, we'll just have the instruction address register set to 1.
Maybe like this is 0001, right? The data is LDA7.
During the fetch cycle, the control unit grabs the data stored at
it's gonna grab the data stored here, right here.
S1 and loads it in.
I have to, you know, I like when I was streaming, like I was streaming, like, you know, in the past, and I had this add-on of pencil add-on for OBS. Oh, OBS forms. Yep. Windows installer zip, Windows zip, Linux zip, macOS zip. Download Windows installer zip. Open the fuck out of him. Windows installer. Wait. Do I have it on Steam? Library. OBS plugins. Store. OBS. OBS Studio. Our 2 desktop overlay. OVR Toolkit desktop overlay. The fuck? OBS. Let's see what it has to offer. Join the playtest. OBS plugins. We don't have it. Let's go. Next. Doc. Next. Install. Finish. I have to put hide docs. You said docs. Basically, the UI will hide additional docs. No. This is for Twitch. This is I have to cancel. Start collection tools. Okay, fuck it. Next time. We're gonna do it next time. I don't wanna turn off the stream, right? Stream now. Stream now. Stream now. Oh, I have to do that personally. Maybe you guys don't see me. Boom. Boom, guys. Holy shit, man. I love tacos too. These are delicious. Those the heck guys are the that's funny. Yo, Yurgi, shout out my boy. Shout out my boy. I was not looking at you. Sorry. I was too involved. I'm not used to, I'm not used to my brother. Sorry. Go stream Arc Raiders. What the fuck are you doing? I don't fucking care, brother. What does it mean? Top fans. Top fan number one. I'm sorry, brother. I'm sorry. I'm sorry.
Instruction register. That's it. The data has been fetched and the control unit waits for the next tick of the clock. Now it's time to decode. Our data contains both an opcode and some information.
Wait. So, this data that I mentioned was LDA7, right? Let me note. Preview, notepad. Save. This was a like there was a 0001 was the and this was LDA7, right? When this goes to in this part, like in instruction register, this is divided like LDA7 in the register in the instruction register. So basically, there's something wrong, yeah? No, not wrong. I mean, opcode and operation, yeah, is divided, not in the like, yeah, Okay, let's go.
Been fetched, and the control unit waits for the next point to load the first instruction. And for our purposes, we'll just have the instruction address register set to 1. During the fetch cycle, the control unit grabs the data stored at address 1 and loads it into the instruction register.
Totally, there are many addresses.
The data has been fetched and the control unit waits for the next tick of the clock. Now it's time to decode. Our data contains both an opcode and some information.
Data contains opcode and some information.
Architecture, the instruction could have a fixed width or a variable width. But to keep things simple, let's say we have 4 bits for our opcode and 4 bits for data.
Okay, so 8 bits.
The control unit takes the opcode and looks up the operation in the instruction table. In this case, it's a load operation.
Opcode is a LD, and the operation is load.
Takes 2 arguments, the source address of the data to load and the target register to load it into. Decoding the operation shows that we're going to load data from address 7 to register A.
Address 7, register A? So A7, not O7, A7. A7 equals. Well, it will 8.
Could have a fixed width or a variable width. But to keep things simple, let's say we have 4 bits for our opcode and 4 bits for data. The control unit takes the opcode and looks up the operation in the instruction table.
So LD is load, like basically that means that, and LD equals LD is opcode code, and load. I think from here it we don't have that one, right? Operation load equals operation. Operation equals load. Load. And here I would A7. Yeah, A7. Yeah.
Case it's a load operation. The load operation takes 2 arguments, the source address of the data to load.
So load operation takes 2 arguments, like there's the arguments,
and the target register to load it into.
Source address of the data to load, and the target register to load it into. So okay, wait, I don't understand. The source address of the data. The source address of the data is not the memory, no? The source address of the data.
Decoding the operation shows that we're going to load data from address.
Load data. Data from address 7 to register A.
To register A. During the next clock cycle, the control unit executes the operation, loading the data in address 7 to register A. We have the number
address 7 to register A. Holy shit. Okay. Oh, guys, I need to show you this though. To show you this. It's important. Everything's important now. Holy. Okay, we're gonna see that now. We're gonna see that now. Okay. So the register A. Yeah. So here we are, guys. Here we are, guys. So this means that we are gonna load data. Load data to from address 7 to register A, and data is right now 3. We're gonna load 3 in here.
3 stored in address 7, and that value is written to register A. When the execution is complete, the control unit increments the instruction address register by 1.
So when it's done, it becomes now here it becomes the 2. We go to address 2
and starts the process over again.
Okay.
On our next fetch, decode, and execute cycle, we will load a value from address 8 to register B and increment the instruction.
Address 8, register B. Yeah, LDB8. Now it's LDB8. 002, LDB8. B8. We're gonna load data. B8 is the instruction register. We're gonna open the operation load. B8 to from 8 to B, and here it's gonna show us 4 when the execution happens.
We now have the number 4.
Execution happens, yeah, and this automatically changes to 3. Let's predict now. In the 3, there's like different operation code. Opcode AD. What opcode AD stands for? Add operator, which is executed to perform addition. Okay, fuck off. We're not gonna do it to that. ADAB. From maybe add from B to A, and it's gonna from B register to A register, and it's gonna become 7 or what?
Stored in register B. The cycle repeats
Wait.
B and increment the instruction address register by 1. We now have the number 4. We will load a unit increments the instruction address register by 1 and starts the process over again. On our next fetch, decode, and execute cycle, we will load a value from address 8 to register B and increment the instruction address register by 1. We now have the number 4 stored in register B. The cycle repeats, but this time the opcode is an add operation.
Yeah, it's add
The
operation.
operation takes 2 arguments, the 2 registers holding the numbers to add together, and it sends that information to the ALU to perform the addition. The ALU accepts the input of the 2 registers and the operation of add. The opcode to add writes the result to the first register in the arguments, so we end up with 3 plus 4, or 7, being written back to register A.
Yep, that's what I said. But B stays. So yeah, in the A it became 7 as we said, but B also stayed as 4. You know?
Cycle.
Now we went to 4. It's WR A9. So now, okay, it's incremented. Right now we are at 0004. We are WR A9. So write from 9 to register A. Okay, write 9 to register A. So I think it's gonna be like vice versa, and it's gonna write 0007 here. I think so.
Code tells the control unit to write a value to memory. The arguments
Yeah,
are
write a value to memory, yeah.
to write to, and then the register containing the data to write. Our value of 7 is written to memory
As we say.
The next memory address has a halt operation, which simply tells the control unit that its work is done until another.
So this is a halt operation, that the work is done until another program is loaded. Okay.
Program is loaded. Our addition has completed successfully, and it took 4 clock cycles to perform the addition. This is a relatively simple example, and there are a lot more operation types that make up the instruction set. How does one know what instructions are supported for a given platform? By consulting the instruction set architecture.
RISC versus CISC. Instruction set architecture, guys.
An instruction set architecture is an abstract expression of instructions, data types, and registers that will be supported by the computer. I say abstract because the ISA is not prescriptive in how the architecture is implemented, only that the components are supported as described. This means that the underlying hardware can continue to evolve and improve with faster clock speeds, smaller transistors, and more cores, while still supporting the same basic instructions. Newer versions of and how the architecture is implemented, only that the components are supported as described. This means that the underlying hardware can continue to evolve and improve with faster clock speeds, smaller transistors, and more cores, while still supporting the same basic instructions. Newer versions of an ISA can include additional instructions, expanded registers, and new data types, but the core promise is that previous versions will continue to be supported, providing forward compatibility of older application binary interfaces. There are some limitations to that statement, but it's broadly true that you can get older software to run on newer hardware if they're using the same ISA. One major area of change is the size of the instruction set. For instance, the original Intel 8086 instruction set had a total of 81 instructions. That's the beginning of the x86 instruction set architecture.
So this is x32, you know, the Windows is right now it's on x64.
A modern x86 processor still supports these 81 instructions. However, the current Intel Software Developers Manual contains thousands of supported instructions. Why so many instructions? Well, let's think about our addition example from earlier. In order to add two numbers together, I not only needed 4 clock cycles, I also needed 4 separate instructions. Those take up 4 address spaces and require someone or something to take the mundane operation of adding 2 numbers and storing the result and breaking that into the 4 separate instructions for the CPU to understand. Early computers were constrained on memory, and there were no compilers translating your high-level programming language to assembly code. The solution was to create more complex instructions that could execute multiple operations while still being expressed as a single instruction. Instead of 4 instructions, we could have one add instruction that takes 2 memory addresses and writes the result to the first address. The CPU still does all the same work, and it takes a similar number of cycles, but it takes up a quarter of the memory space and makes writing the code easier for programmers. This trend toward creating more complex
So complex instruction set or reduced instruction set? CISC, RISC.
Led to CISC, or Complex Instruction Set Computers. While CISC was an excellent solution for computer programmers of the 1970s and 80s, it did have its drawbacks. One was an absolute explosion in the number of instruction variants that needed to be supported. The second was a rise in the complexity of the hardware that had to support all these additional operations. The solution to the CISC challenge was to vastly reduce the instruction set and complexity with RISC, or Reduced Instruction Set Computers. RISC chose to stick with relatively simple instructions, all of which could be completed in a single clock cycle. RISC might take up more clock cycles and more memory to perform the same operation, but it vastly simplified the hardware design and it allowed a greater degree of control over how an operation was executed. It also enabled better pipelining, which we'll touch on in a moment. There were 2 big improvements that facilitated the rise of RISC: the massive drop in the cost of memory and the rise of high-level languages with excellent compilers. Programmers no longer had to be so conservative in their memory usage, and compilers—
I think that now there's a rise of prices in the RAM.
easier to write for RISC, given the reduced number of instructions to choose from.
RISC.
RISC and CISC were both looking for ways to make programming and computing more efficient. But how do you also increase performance? One potential answer is pipelining, which I'll try to explain through analogy.
Benjamin. This, guys, this is what we really need. I think so. What do you think? No one's here, by the way. It's okay.
RISC and CISC were both looking for ways to make programming and computing more efficient. But how do you also increase performance? One potential answer is pipelining, which I'll try to explain through analogy. The perennial analogy for pipelining is that
Parental.
of doing laundry.
What's perennial and parental analogy?
Something I can certainly relate to, having 3 children. The amount of laundry is, frankly, ridiculous. Imagine we have 4 loads of laundry to do, and each load has 3 distinct steps: wash, dry, and fold. Washing takes 30 minutes, drying takes 40 minutes, and folding takes 20 minutes. I don't fold that fast. That's 90 minutes per load. And if I did each of those loads in serial, it would take me 6 hours to get them all done.
But we are gonna do it like
That's
together.
not how you or I would do it.
So this means that, you know, instead of we have 4 like laundries, right? Instead of doing it like separately, we're gonna do like everything. And I think the folding is gonna be different, you know.
You would start the first load in the washer, and as soon as it was done,
Like
start
wash everything, dry everything, and fold everything.
load while the first load is in the dryer. When the first load is done drying, you can start the third load in the washer, dry the second load, and fold the first. It's a pretty intuitive pattern, and the result is, instead of taking 6 hours, my 4 loads now take only 3.5 hours.
Okay.
That is some serious time savings. Now let's swap the wash, dry, and fold cycles with our fetch, decode, and execute cycles. When my CPU is doing a decode, the fetch and execute portions of the control unit are idle, and idle time is wasted time. Pipelining stacks the cycles on top of each other, so every clock cycle, the control unit is doing all 3 simultaneously. This works especially well for RISC processors, since all instructions execute in a single clock cycle. For CISC, it gets a little more complicated. Pipelining can also be expanded out to multiple cores, which almost all modern computers have. Each core can execute pipelines simultaneously, thus further increasing the performance of the computer overall. However, there are some limitations and hazards to pipelines that we should talk about.
Okay. Hazards in pipelining and solutions.
Stacking instructions in a pipeline can be a great way to improve the performance of a CPU, but it can also lead to conflicts in both the hardware and the program. The first conflict is that of 2 instructions trying to access the same hardware resource at the same time. If instruction A is in the execute phase and trying to write a value to a memory address, and instruction C is in the fetch phase trying to read from that memory address, we have a hardware conflict, and the control unit needs to deal with it.
So no, wait, I don't understand.
And instructions C is in the fetch phase trying to read from that memory address, we have a hardware conflict, and the control unit needs to deal with it. You can also have dependencies between instructions. Imagine instruction A is executing an addition of registers 1 and 2 and storing the value in register 3. And instruction B is decoding an addition that adds the contents of register 3 and 4, storing it in register 5. There is not yet a value in register 3 until instruction A finishes its execution. So the pipeline will stall while it waits for the value to be available.
Okay.
The solution to these 2 problems is code reordering, something that is usually handled at the compiler level. Rather than instruction A and B running one right after the other, the compiler looks for other instructions that do not have a dependency or a conflict and puts them between A and B, so A is finished before B must be run. This is one of many optimizations that modern compilers will make when evaluating your code. Another cause for pipelines to stall is when a conditional statement appears in the code. The condition is usually called a branch, because the code could go one of 2 ways depending on some value. If that value is not yet known, the CPU doesn't know what it's going to do next, so it can't stuff its pipeline. Imagine a loop that does some work and then decrements the value stored in a register. When the value is 0, the loop should end and the program continues on its merry way. The CPU doesn't know exactly when that will be, so it has trouble building out an efficient pipeline. The solution is for the CPU to guess. Yeah, just guess. Also known as branch prediction, probably because it sounds a little bit better. but it will load the next few lines of code based on the guess or prediction that it makes. If the CPU is right, the pipeline executes and all is well. If it turns out to be wrong, the registers need to be cleared and the pipeline run again. This might not seem like a great strategy, but modern processors can successfully predict the correct branch about 90% of the time, and that is some serious time savings. And time is the name of the game, well, sort of. We should probably build some more formal definitions around what metrics we're measuring when it comes to CPU performance.
Holy shit, guys. This was not.
If there's
I
one
understood
thing
half. I didn't understand half.
drives performance of CPUs, it is clock speed. Each tick and tock of the clock moves the pipeline forward. So when we're trying to figure out how long our program is going to take, it all comes back to how fast the clock is moving and how much the CPU can do with each cycle. This formula can help you understand what's going on. The time it takes for your program to complete is the time it takes for a single cycle to complete times the number of cycles it takes for an instruction to complete on average, times the number of instructions in a program. Now that's a little esoteric, so let's add some actual numbers to this.
Nanoseconds, yeah,
Let's say I have a
nanoseconds.
program that consists of 20,000 instructions. And since I'm using a RISC processor, each instruction is going to take, on average, 1.5 cycles to complete with pipelining. And my clock is running at 1,000 cycles per second, which is 1 cycle every millisecond. That's 1 millisecond times 1.5 cycles per instruction times 20,000 instructions, which comes out to 30 seconds.
Okay.
How could I improve this performance? Well, I have a few levers to pull. I can make the clock go faster.
Okay.
I can reduce the cycles per instruction, or I can reduce the number of instructions per program.
Mm-hmm.
RISC architectures have simpler instructions, so you need more of them, but you need less cycles to complete each one. CISC architectures have more complex instructions, so you get less of them, but you also need more cycles to complete each instruction.
Mm-hmm.
The performance of a program might be dependent on which architecture and which compiler does a better job of sequencing the instructions that are in your program. Mm-hmm. Pipelining, branch prediction, and a method called super pipelining, along with multiple cores, are other ways to tweak the performance numbers in our favor by lowering the number of cycles per instruction. There's one more thing we can do, and that's make sure that the CPU is never waiting on another component for information. And that's a function of caches and memory.
Registers, caching, and memory interactions. Okay. That's the last part of the CPU.
As we've seen in our examples, registers play a critical role in the functionality of a CPU. You can think of registers as scratch space for the CPU to temporarily store data, instructions, addresses, or anything else that will need quick and repeated access to.
Okay.
Registers are the top of the memory hierarchy and usually address differently than main memory. Modern CPUs have several types of registers that can house different kinds of data. Some examples are data registers for small data structures, address registers that will hold main memory addresses, floating point registers for the storage of floating point numbers, vector registers for so-called single instruction multiple data instructions, and there are also general purpose registers that can hold data, addresses, or floating point values. The exact type and width of registers in a system is determined by the CPU architecture and design. An x86 64-bit architecture typically has 16 general purpose registers and a width of 64 bits each, and 16 floating point registers with a width of 128 bits, or wider depending on the generation of the chip.
Vader Hub has been sold. Yes. It was sold or crashed. Vader Hub. Is it this one? Who's the owner? Hmm. The news. Trial. First cases. Traders. What the fuck? Let me. Where was that? General. The fuck? Fuck. Fuck off, man.
Registers sit closest to the CPU and have the fastest response time, but they are also extremely limited in capacity.
The
1
fuck
kilobyte.
I have on my forehead. This is going to get fun. This is going to get fun after I learn something, guys, so I can teach you as well. After we get our hands on labs, right? Actually, you know what I can do? I can just like learn this stuff by myself, and just do labs with you, and that's all. Maybe that's
Which is why so many instructions first load data into register
this guy. Does it have? This guy doesn't have labs, I think.
before performing operations. The data they load is typically coming from main memory, which is far more plentiful in capacity, but far slower in access times. My desktop, for instance, has 64 gigabytes of memory and an average latency of 500 nanoseconds. Now that might seem wicked fast, but the average latency for a register is in the sub 1 nanosecond range.
Okay.
If I were to convert that to seconds, and it takes 1 second to get data from a register, it would take 8.3 minutes to get it from memory.
Okay.
If a CPU is waiting for data from memory, it is waiting a comparatively long time, and having an idle CPU is no good. The solution is to add another place to stash data that is closer to the CPU and faster to access, and that is what cache does. A lot of data CPUs access is sequential in nature. So if you're reading the contents of a file stored in memory, chances are you're going to read line 2 after line 1. Caches on a CPU make an educated guess about what you're likely to read from memory next and preload it into the cache in anticipation that the CPU is going to ask for that information next. When the CPU requests a memory address that is already in cache, the request is short-circuited and answered by the cache. That's called a cache hit, and cache hits are good. If it's not in the cache, that's a cache miss, which is bad, but don't worry. the missed data will be added to the cache so it won't be a miss on the next time around. Caches have a latency of 1 to 10 nanoseconds in general, so they're slower than registers, but they're also way faster than main memory, and they have more capacity than the registers. We'll talk more about caches in the next module.
This is memory and storage, guys. Yeah, actually, I feel bad for you guys. I shouldn't be learning theory from you, like with you. I should be doing labs with you, only labs with you. But I came to a question. What's gonna be the lab? You know, like about this. Don't know.
Although the CPU is the core of what makes a computer, it wouldn't be able to do much without memory and storage. You might be wondering, what's the difference between memory and storage? Aren't they kind of the same thing? I'll admit that the boundary between the two has been getting fairly hazy, but there is one main distinction.
Okay.
Memory refers to hardware that the CPU can directly access through the control unit. When the fetch portion of the CPU cycle asks for the instructions and data stored at an address, the address refers to a location in main memory. So when we're talking about memory, we're talking about the addressable space the CPU has access to. Storage, on the other hand, is anything housing data that the CPU cannot directly access. Instead, the CPU relies on external components that are dedicated to reading from those hardware types. For instance, to read in data from a hard drive, the CPU will work with the Direct Memory Access Controller, DMA, and I/O controller to request a data transfer to memory. And then it lets the DMA and I/O controllers take over and wait until the data is loaded into memory. Only then can the CPU access that information directly and start using its contents. The main characteristics that define memory for a computer are low latency access, limited capacity, and volatility. When we talk about low latency, that is relative to the other components in the computer, like registers and long-term storage. Memory.
Yeah, in this picture, CPU has access to the RAM, right? But it doesn't have access to the hard disk, which is a storage, and the CPU has access to DMA and has access to the RAM. It communicates with DMA. The DMA communicates with the storage. Okay, gets the data, sends it to the RAM, and then CPU has access to the RAM.
Generally be an order of magnitude slower than the registers of the CPU and several orders of magnitude faster than the storage. In a modern system, registers operate. Talk about the main characteristics that define memory for a computer are low latency access, limited capacity, and volatility. When we talk about low latency, that is relative to the other components in the computer, like registers and long-term storage. Memory will generally be an order of magnitude slower than the registers of the CPU and several orders of magnitude faster than the storage. In a modern system, registers operate with sub-nanosecond latency, and main memory sits in the hundreds of nanoseconds. Your SSD, even a really fast one, will have latencies closer to the micro or millisecond range. Memory is also limited in capacity relative to storage. My current system has 64 gigabytes of RAM in it, which is a decent amount, but it also has 2 terabytes of storage, which is 32 times as much. Memory is usually volatile in nature too, meaning that it requires constant power to hold data.
Okay.
When power is removed, the memory's contents cease to be,
Okay.
which you know all too well if your computer suddenly got unplugged without saving anything. The act of saving a file is essentially moving data from volatile memory to persistent storage.
Which is
Now, there are recent
hardest.
advancements in hardware that are shaking up the volatile nature of memory. For instance, Intel's Optane memory made use of persistent memory in the same physical slots as DRAM while maintaining similar access speeds. To balance the differences between memory and storage, there is a hierarchy followed by all computing architectures.
Memory has speed versus capacity. Yeah, speed, executed registers, cache, RAM.
We touched on the hierarchy of memory and
SSD.
storage in the previous module about the CPU, highlighting the registers, CPU cache, and main memory. Storage simply adds more tiers to the hierarchy. Each tier is a trade-off between speed, cost, and capacity. Generally speaking, the higher in the hierarchy we go, the faster and more expensive the component is, and the lower its capacity. So registers are the fastest, having sub-nanosecond speed, and the most expensive. If you want bigger or more registers on your CPU package, you're going to pay a lot more for just a little bit more capacity. That trend continues with the CPU cache, main memory.
So how do I understand? So like CPU, i9 what? The Core i9. Gamers G, fuck man, I don't want fucking Gamers G. I want fucking this. So 14900K. Desktop processor, okay. How do we know how much registers does it have? Threads, cores plus 16 E-cores, P-cores, E-cores, 24 cores. Clock speed of clock speed of up to 6. It gives you smoother gameplay, higher frame rates, and combined with intelligence. Okay. What's mine? Let's see. System about 2.6. That's not good. Not good. Not good.
Memory like Optane down into traditional storage, which has a ton of options. There's NVMe SSDs, USB thumb drives, spinning hard drives connected with SATA or SAS, DVDs, and even magnetic tape. The trade-offs continue in the same manner, with either costly speed or cheap capacity. In fact, there's even striations within the CPU cache itself.
Okay, cache systems and optimization.
As we covered in the previous module, CPU cache is a feature of CPUs that provides low latency access to main memory by storing recently accessed information or information that is likely to be accessed.
So now, when you're gonna look at the clock, like the CPU, you know what clock speed means. You know the time it takes for one operation to one cycle. You know that's a clock speed. One cycle. That's a clock speed. Okay.
When a request is made for data at a main memory address, the CPU checks first if that data is sitting in cache.
Okay.
This is called a cache hit. If the data is not present in the cache, that would be a cache miss. To make things even more complicated, there are multiple levels of cache on a CPU, usually referred to as L1, L2, and L3, and sometimes even L4. Lower numbers have lower latency and less capacity, so they're faster, but there's also less space available. Take my current desktop as an example. I have 384 kilobytes of L1 cache, 12 megabytes of L2 cache, and 19 megabytes of L3 cache. My CPU has 12 cores, and the L1 and L2 cache are spread evenly amongst those cores.
Okay, so it depends how. Okay, it's about the cores. It's about the cores. The cache. Cache means cores.
Each core has 32 kilobytes of L1 and 1 megabyte of L2 cache dedicated to that core. The 19 megabytes of L3 is shared across all the cores. The latency of L1 and L2 is in the 1 to 10 nanosecond range, and L3 is in the tens of nanosecond range.
Okay.
Compared to main memory, which is usually in the hundreds of nanoseconds, cache hits can seriously improve the performance of a computer by keeping the CPU from stalling out, waiting for data to be loaded from main memory, or heavens forbid, from some storage device. Caches are not just for reading data, they can also act as a proxy for writing to main memory.
Okay.
When the CPU needs to write some information to main memory, that request can be intercepted and written to cache instead. The CPU can then blissfully move on to the next task, while the cache is now responsible for actually updating main memory. This is accomplished through a dirty bit. On write, the cache block has its dirty bit set to 1, meaning that the cache block's contents no longer match the corresponding block in main memory. Before a cache block is purged to make room, the dirty bit is checked, and if it's set, the data is written onto main memory. This strategy is called a write-back cache policy. If you wanted to ensure immediate consistency between the cache and main memory, you could force a write-through cache policy. That does introduce some latency, but it also ensures consistency.
Okay.
Why does consistency matter? Because of the challenge of cache coherence. Cache coherence deals with whether a given cache block is valid or not. In other words, does it contain the most current value for its corresponding memory block? For single-core processors, this is not a big deal, as there's really only one way for main memory to be modified. But for multi-core processors, this becomes a huge headache. Remember that the L1 and L2 cache on a processor are core-specific. So imagine that Core A and Core B both have a cache block for address OX042, where food equals tacos. Core A performs a write, changing the cache block to food equals pizza. Core B will still have the old and now invalid value of food equals tacos. And if the cache policy is write back, main memory has the same stale value as well. How do we solve this? There are several ways to do this, but one of the most common is the cache coherence protocol MESI and a shared bus or cache line directory. MESI stands for Modified, Exclusive, Shared, and Invalid. These values are applied to each cache block and checked before a read or write action occurs. Repeating our example, Core A accesses OX042 and gets a cache miss. No other caches have OX042 stored, so it fetches the value from memory and labels the block as exclusive in its cache. Core B accesses OX042 and gets a cache miss
It's
as
not
well.
exclusive anymore.
It sends a request on the cache bus line, and Core A snoops the request and responds with the current value.
Yep.
Core B gets the copied value and sets its cache block to shared. And Core A also sets its cache block to shared. Now Core A wants to write a new value to OX042. Since it's in shared mode, it signals to all other shared instances through the bus that they should switch to invalid. Then it writes the new value and changes its cache block to modified. At the end, Core A's cache block is modified, Core B's cache block is invalid, and main memory still has the old value.
Yeah.
We could keep going with this example, but I think you get the point. Cache is incredibly powerful and it's critical to the performance of modern computing, but it also can add a layer of complexity with cache coherence.
Okay. Virtual memory of paging.
As you may have noticed, main memory on a computer system is a limited and highly valuable resource. Programs that want to run on the CPU need to load their data and instructions into main memory. Anything that isn't loaded into memory will need to be fetched from storage later. which leads to lag and performance issues with the program. In an ideal world, every program would be able to load their entirety into memory and
So I think that in the later section, I will always try to. I have to think about it. I don't know. I have to think about it. Like
best
I don't know. Like
performance.
right now,
However,
my
memory
viewers
is
doesn't
a
do
scarce
anything.
resource, one that was even scarcer in
Like
earlier
watching me watch someone like who can't even see.
computer systems. The solution to this conundrum is virtual memory. Virtual memory is an abstract
What was the deal?
main memory on a computer system is a limited and highly valuable resource. Programs that want to run on the CPU need to load their data and instructions into main memory. Anything that isn't loaded into memory will need to be fetched from storage later, which leads to lag and performance issues with the program. In an ideal world, every program would be able to load their entirety into memory and get the best performance. However, memory is a scarce resource, one that was even scarcer in earlier computer systems. The solution to this conundrum is virtual memory. Virtual memory is an abstraction that presents a virtual memory space to each running program. This allows each program to request as much memory space as it wants, within limits, letting a memory management system take care of the actual allocation of physical memory. There is also a side benefit that each program operates in a sandboxed memory space that other programs should not be able to access, which adds security and stability. So if our computer system is offering up virtual memory and that exceeds the amount of physical memory, where does it store that additional data? It uses local storage that is designated as swap space. To make virtual memory work, the system uses a mechanism called paging. Paging divides both the virtual memory and physical memory into fixed size blocks. For virtual memory, they're called pages, and physical memory, they're called frames. When a program accesses a virtual address, the memory management unit maps that address to a frame in physical memory. If the page is not currently loaded into RAM, it triggers a page fault, and the system pulls the data from the swap space on disk into a free frame of physical memory. But using swap space comes at a cost. Storage is orders of magnitude slower than main memory. When your system starts relying heavily on virtual memory because it's out of physical RAM, you get what's known as thrashing. That's when the system spends more time swapping pages in and out of memory than it does actually executing code. If you've ever had your computer slow to a crawl when you open too many programs at once, then you've seen thrashing in action. You might also hear about segmentation, which is another memory management strategy. Instead of using fixed size pages, segmentation divides memory into variable size segments based on the logical divisions of a program, like code, data, and the stack. While this allows for more meaningful organization, it also introduces complications like external fragmentation, which is why modern systems tend to use paging, or a hybrid approach, sometimes called segmented paging. Now, since there's not an infinite amount of physical memory, the operating system has to decide which page to evict from RAM when it's loading a new one. That's where page replacement algorithms come in. We have first in, first out, which is the simplest. Just evict the oldest page. Then we have LRU, or least recently used. This tries to be a little smarter by tracking which pages haven't been used in a while, assuming that pages used recently are more likely to be needed again soon. Others like clock, optimal, or even random exist, each with their own trade-offs in terms of complexity performance. The effectiveness of these algorithms can have a significant impact on the system performance. A well-tuned memory management system will minimize page faults and ensure that the most relevant data stays in RAM. Virtual memory, while not a substitute for having enough physical RAM, provides a vital safety net that keeps systems stable and multitasking capable even under heavy load.
This is really got like a little bit complicated, guys. I'm not gonna lie.
As you may have storage has come a long way from the clunky magnetic monsters of the past. Early systems used magnetic tape and even punch cards, yes, punch cards, to store data. Then came spinning disks or hard disk drives in the form of washing machine-sized devices holding giant spinning platters. Later models shrunk down the device's size, increased the platter count, and packed in more bits. For decades, these were the dominant form of storage. Hard drives store data magnetically on spinning platters, with a read-write head that moves mechanically to access different parts of the disk. While the capacity and the cost per gigabyte were unbeatable for a long time, these drives have one big bottleneck: speed. The mechanical nature of hard drives makes them much slower and more prone to wear and tear over time. Enter solid-state drives. Instead of using moving parts, SSDs use flash memory to store data, which allows for significantly faster access times, greater durability, because there's no spinning parts to fail, and better power efficiency. SSDs have basically revolutionized consumer computing. Boot times that used to take minutes are now counted in seconds. But not all SSDs are built the same. The traditional SSDs connected via the SATA or SAS buses, which caps out their performance. Newer SSDs make use of NVMe or Non-Volatile Memory Express, a protocol designed for flash storage that connects directly to the PCI Express bus, allowing for much higher throughput and lower latency. If you've got an NVMe SSD in your system, you're probably already enjoying the benefits: faster game load times, quicker file transfers, and snappier application launches. Under the hood, SSDs rely on
How to determine SSD type? Control Shift ESC. Okay. Personal tab, click disk. Okay. Look for SSD base signal, sometimes shows NVMe. Yep, we got it. We got it. NVMe. Yep.
memory, specifically NAND flash. The type of NAND used and
Okay.
snappier application launches. Under the hood, SSDs rely on flash memory, specifically NAND flash. The type of NAND used, SLC, MLC, TLC, or QLC, affects performance, endurance, and cost.
Okay.
SLC, or single level cell, is the fastest and most durable, but also the most expensive. Quad level cell, QLC, is cheaper and higher capacity, but wears out faster and is slower to write. MLC and TLC are somewhere in between. As storage is cheaper and higher capacity, but wears out faster and is slower to write. MLC and TLC are somewhere in between.
Okay. Let's see. Hardware resources. Force hardware IOs. You see, this IOs, it was talking about memories. Force hardware, DMA, conflicts and sharing, system killers, real-time clocks, and components. System sound about display, shared input, keyboard, pointing device, modern network, for storage, drives, disks. SLC, QLC, NTFS, was? Disk. The fuck? MZV, CCCI. IDE, these drives. How to check cells. Yeah. The indirect, how to check the method, use software, best way. HV info steps, crystal disk info. Opens the app, look for an NN type, sometimes flash type. Show TLC, okay, if it doesn't show an NN type, very common, then use method to Google the method. Or in the PowerShell, okay, the PowerShell, run as administrator, and get Pysicle. Pysicle. Okay. Friendly names, okay, that. Size, GBs, file, Campo, operations, okay, health service, has usage, auto select serial number. PCO. What? Find your SSD model. Perform this, okay. Model, and the type. What? The type is ST, yes. We have serial number, family number, okay. Can it be written somewhere, motherfuckers? Motherfuckers. I wrote it, brother. It doesn't show. It does not show the cell type. Okay, NAND type, NAND type. It's TLC. Okay, it's in the middle. Triple level C flash memory. It's triple. It's triple. It's not quad, but it's triple. Okay.
As storage needs to continue to grow, so do the innovations. 3D NAND stacks flash memory cells vertically to increase density without shrinking cells further, which would reduce their reliability. Then there's Intel Optane, which uses 3D crosspoint technology to blur the lines between memory and storage. Now, Optane has since been retired, but the general idea has been taken up by storage class memory. SCM aims to combine the best features of RAM and storage: fast, byte addressable, and non-volatile. Imagine booting your system and everything is exactly where you left it, even the open browser tabs. We're not quite there yet, but SCM is pushing in that direction. The story of storage is a constant struggle between cost, durability, speed, and capacity. While newer forms of storage have appeared, you can still find many of the older technologies present to solve for different needs. Magnetic tape, hard disk drives, and even floppy disks are still out there, although for most people that last one is just the save icon.
Input output systems and bus architectures, guys. These IOs.
We've talked a lot about memory and storage, but how do all these components actually communicate with the CPU? That's where the input-output subsystem comes in.
What?
We've talked a lot about memory and storage, but how do all these components actually communicate with the CPU? That's where the input-output subsystem comes in. It's the bridge between the CPU and the rest of the world, whether that's reading from a keyboard, sending data to a printer, or loading textures from an SSD for your favorite video game. I/O devices come in all forms. Storage devices like hard drives, SSDs, and USB flash drives, peripherals like keyboards, mice, displays, and printers, and networking devices like Ethernet cards or Wi-Fi.
So I/O devices are the storage, peripherals, network.
To coordinate all this activity, computer systems use a set of buses, essentially communication pathways inside the motherboard. The classic architecture breaks this down into three main buses. There's the address bus, which carries the memory addresses of data that the CPU wants to read or write. There's the data bus that carries the actual data to and from the CPU, and the control bus, which carries control signals like whether it's a read or write operation and coordinates access among devices. Then we have peripheral buses, which are highways that allow devices to plug into and talk to the system. A few examples are serial ATA or SATA, which is used mainly for connecting older or budget-friendly hard drives and SSDs. It's still widely used, but it's being pushed out in favor of PCIe, which is the Peripheral Component Interconnect Express, or just PCI Express. This is a high-speed interface for connecting GPUs, SSDs, network cards, and more.
We have this
It's
PCI.
the go-to for performance-critical hardware.
We have
The
this
current
one.
standard of PCI Express 6 has a theoretical bandwidth of 8 gigabytes per second per lane in each direction. A full 16-lane slot could potentially give a GPU 256 gigabytes per second of bidirectional transfer speed. That's not bad. Then there's the Universal Serial Bus, or USB. This is the Swiss Army knife of ports. It's the one you're probably most familiar with, since it tends to include external ports you can use to plug in your thumb drives, keyboards, and pretty much anything else. The current standard of USB 4 offers transfer speeds of up to 120 gigabits per second in one direction, which is not as fast as PCI Express, but it's still plenty to mouse around. The efficiency of your I/O system has a direct impact on your overall system performance. A blazing fast CPU doesn't help much if it's constantly waiting on slow I/O operations to finish. This is called being I/O bound, when the system's bottleneck isn't the processor, but the speed at which it can read and write data. Operating system and application designs do their best to move data closer to the CPU through virtual memory and caches, but ultimately they do need to load that data from persistent storage, which may become the choke point without proper planning and design. That's why high-performance systems pay special attention to I/O architecture. Choosing the right buses and optimizing I/O workflows is just as important as having fast processors or lots of RAM. A well-balanced system ensures data flows smoothly from storage and peripherals to the CPU and back without unnecessary bottlenecks.
Okay, direct memory access, DMA, and I/O performance optimization. Okay.
If the CPU had to personally handle every single data transfer and I/O operation in the system, it would never get anything else done. That's where direct memory access, or DMA, steps in. DMA allows I/O devices to read and write to memory without involving the CPU for every byte of data. Instead, the CPU kicks off the transfer by configuring the DMA controller with the source, destination, and the amount of data. After that, the DMA controller takes over, moving the data in the background while the CPU continues with its other tasks. Once the transfer is done, the DMA controller can notify the CPU, typically through an interrupt. This offloading is critical for high-speed data movement, especially with large files, real-time audio and video streams, or storage devices transferring data to memory. Without DMA, you'd have the CPU constantly stalled, waiting on slow I/O processes. Now let's talk about how systems manage I/O in general. There are a few models.
Okay, we'll put it out.
There's programmed I/O. This is the most basic and CPU-intensive method. The CPU continuously checks if a device is ready by polling it. When it is, it transfers the data itself. It's simple, terribly inefficient. Then there's interrupt-driven I/O. Instead of constantly polling, the CPU asks the device to send an interrupt when it's ready to transfer.
Okay.
This saves CPU cycles, but each interrupt still takes some overhead in the process. Then there's DMA-based I/O. This is the most efficient. The CPU initiates the process and then steps aside, letting the DMA controller handle the heavy lifting. Beyond these, there are buffering and caching techniques that further improve I/O performance. Buffers are temporary memory areas used to smooth out the data flow between devices that may be operating at different speeds. For example, when streaming a video from disk to RAM to GPU, each stage may use its own buffer to prevent hiccups. Caching, similar to what we discussed earlier with memory, can also be applied to I/O. Frequently accessed
You know,
files.
sometimes you hit the point that let me just code, but like, come on, man. I don't have to understand it, but we have to, guys. Somehow, like at least a little bit, we have to understand this.
States or data can be kept in fast access memory to avoid hitting the slower storage every time. Together, these techniques, DMA, buffering, and caching, form the backbone of efficient data handling in modern systems. They ensure that your CPU doesn't get bogged down and that data moves smoothly between devices, memory, and processing units.
Okay, brother. Last model, assembly installed.
We've spent a lot of time talking about the architecture of computer systems. Memory, storage.
Let me check something.
And the CPU itself.
Hungry.
But now we're shifting gears to look at the why and how of making your code and systems run faster, smoother, and more efficiently. Welcome to performance optimization. Why does this matter? Because not all code is created equal. You can write two versions of a program that do the exact same thing, but one might run in a fraction of the time and use half the memory. And in the real world, especially at scale, that difference is huge. Performance optimization can mean the difference between a smooth user experience and a frustrating lag fest. Or in high performance computing, it might mean saving millions of dollars in compute costs. Optimization isn't just about getting the most out of the CPU. It's also about understanding the entire system, how data moves through memory, how often your storage stalls waiting for I/O, how cache-friendly your loops are, and whether your compiler is generating efficient machine code. It's about turning software into something that really plays well with the hardware. There are a lot of factors that affect performance, but here are some key ones. CPU efficiency, which is how well your instructions are pipelined and parallelized. Memory access patterns, which is how often your code causes cache misses or memory stalls. I/O latency, how fast your program can read and write data from storage or peripherals. Compiler optimizations, what your compiler is doing behind the scenes to make your code faster. And instruction set usage, how low-level instructions map to what you write in high-level languages. The thing about optimization is that it's always a balancing act. You can optimize for speed and end up with code that is unreadable and impossible to maintain. Or you could chase hardware-level tricks that only benefit act. You can optimize how low-level instruction code causes cache misses or memory stalls. I/O latency, how fast your program can read and write data from storage or peripherals. Compiler optimizations, what your compiler is doing behind the scenes to make your code faster. And instruction set usage, how low-level instructions map to what you write in high-level languages. The thing about optimization is that it's always a balancing act. You can optimize for speed and end up with code that is unreadable and impossible to maintain. Or you could chase hardware-level tricks that only benefit one specific system. The best performance tuning is thoughtful, targeted, and backed by real data. One of the biggest ways modern CPUs can boost performance isn't by making individual instructions faster, although that does help, it's by doing more at once. That's where pipelining and parallelism come in. We covered pipelining in a previous module, but just to review, instead of waiting for one instruction to finish all three stages of execution before starting the next, pipelining allows the CPU to begin a new instruction at every clock cycle. While instruction 1 is being executed, instruction 2 might be being decoded, and instruction 3 fetched, and so on. The idea is to keep all parts of the CPU busy, just like a factory where every worker handles one specific step of a process. The more efficiently instructions move through the pipeline, the higher your instruction throughput, and the better your overall performance. But things aren't always smooth. You've got pipeline hazards, like we also talked about, data dependencies, control flow changes, think branches, or structural conflicts that can stall progress. That's why modern CPUs have complex logic to predict branches, reorder instructions, and keep the pipeline full. Now, beyond pipelining, there's parallelism, which is about doing completely different tasks at the same time. This can happen at multiple levels. There's instruction-level parallelism, where the CPU reorders instructions or executes multiple independent instructions at once. There's data-level parallelism. This is especially useful in graphics and scientific computing, where the same operation is applied across lots of data. Then there's thread-level parallelism. This is multiple threads running in parallel on different cores. That is where multi-core processors come into play. Instead of one core doing all the work, your system might have 4, 8, or even 32 cores, each capable of running its own thread or even multiple threads via hyperthreading. Hyperthreading lets a single physical core act like two logical cores by sharing execution resources. It's not quite double the performance, but it does help keep the CPU busy when one of the threads is stalled. Of course, parallelism isn't free. It introduces complexity, especially around synchronization, shared resources, and managing concurrency. But when it's done right, it can drastically reduce runtime for tasks that can be split up and run simultaneously. The ability of a program to run in multiple threads is usually the result of its coding, and not a guarantee made by the operating system and the underlying hardware. Many older applications that weren't written with multiple cores and threads in mind won't see a massive improvement in performance on a modern system, since they're still restricted to a single thread at a time. Determining how applications are performing and finding areas of improvement is all part of performance metrics and analysis. How do you know if your optimization efforts are actually working? That's where performance metrics come in. You can't improve what you don't measure, and in performance tuning, solid metrics are your map and compass. Let's start with the basics. Remember that formula we looked at earlier? That formula still applies, but there's more to performance metrics than just execution time for a single program. Here are some of the key metrics you'll encounter when evaluating system performance. Execution time is what we were trying to determine with the formula. How long does it take your program to run? Lower is better, and it's often broken down into user time, system time, and real wall clock time.
I don't know. Sometimes I'm just lost, guys. Fuck
How do you
ADHD.
know if your optimization efforts are actually working? That's where performance metrics come in. You can't improve what you don't measure, and in performance tuning, solid metrics are your map and compass. Let's start with the basics. Remember that formula we looked at earlier? That formula still applies, but there's more to performance metrics than just execution time for a single program. Here are some of the key metrics you'll encounter when evaluating system performance. Execution time is what we were trying to determine with the formula. How long does it take your program to run? Lower is better, and it's often broken down into user time, system time, and real wall clock time. CPU utilization is what percentage of CPU time is spent doing useful work. If your CPU is idle or waiting on I/O, you may have an inefficiency that's not related to the CPU itself. IPC, or instructions per cycle, is how many instructions does the CPU complete per clock cycle. A higher IPC usually means better CPU utilization, but remember, it also depends on the instruction set architecture being used. CISC may have lower instructions per cycle, but end up completing faster. Cache miss rate is how often does the CPU fail to find data in the cache and have to go back to slower memory. High miss rates are a red flag for poor data locality. Reading from memory can take 50 times longer than reading from cache. Branch prediction
Cache
accuracy.
miss rate. How to determine my cache miss rate? My cache miss rate. GPT. Low level hardware metric. Intel VTune profiler shows misses miss rate percentage used by engineers and performance analysts. Okay. Intel VTune profiler. VTune profiler. This is like standalone, though as a part of the toolkit. Get it now. Okay. Do we need the Intel Essentials? No. C++ Essentials. Deep Learning Essentials, what please? Holy shit. You can download the standalone as well. I get this shit, guys. It's cool.
To do with your code. If it has a lot of branching in it, mispredictions can cause pipeline stalls. Measuring how often the CPU guesses right can give you insight into the control flow efficiency that's present in your code. Memory bandwidth measures how much data can be moved between memory and the CPU in a given amount of time. This becomes critical in memory-intensive applications. To measure these metrics, we use profiling tools and benchmarks. Profilers like Perf, gprof, Intel vTune, or Visual Studio's diagnostic tools help you see where your program is spending its time and what's eating up CPU cycles.
Okay.
You can also use system-wide tools like Top, HTOP, or Task Manager for a quick look at utilization and load. When you're analyzing...
So basically, but what about like different like operation systems? What about Linux? It's like, okay, we're gonna use Intel for the Windows, right? But I can no, it's not different. It's like the operation system uses like the CPU. Oh my god, I'm so dumb, guys. Sorry, I'm so sorry.
Always start by identifying bottlenecks. Is the CPU waiting on memory? Is I/O the culprit? Are there too many context switches or cache misses? Targeting the right problem can save hours of chasing the wrong fix. Also, keep in mind, metrics don't exist in a vacuum. Optimizing for one metric can hurt another. For example, reducing execution time might increase memory usage. That's why evaluation isn't just about raw numbers, it's about understanding the trade-offs and choosing the right priorities for your application.
Okay. So it's varied across the applications, right? So when we configure the application, we choose how it does that.
No matter how high level it starts, gets turned into something the CPU can actually understand and execute. That something is machine code. And just one step above that, we've got assembly language, a kind of human readable representation of machine instructions.
Mm-hmm.
If you've ever written a program in C, Python, or Java, you're writing instructions for a compiler or an interpreter to translate into something lower level.
Mm-hmm.
But the further down you go, the closer you get to the metal and the more control and responsibility you have over what actually happens at the hardware level. Assembly language is specific to a processor's instruction set architecture, which defines the commands the CPU understands. Common ISAs include x86, ARM, and RISC-V. In assembly, you work with operations like move, add, compare, and jump, directly manipulating the CPU's internal components like registers and the stack. Registers are the fastest form of storage, and they're sort of the CPU's scratch base. They're used for holding operands, addresses, and intermediate results. Working directly with registers in assembly is usually unnecessary, but it can give you real insight into how your program executes. Then there's the stack, which the CPU uses for managing function calls, local variables, and return addresses. Assembly gives you control over how the stack is used, including manually pushing and popping values, handling function prologues and epilogues, and managing memory layout, skills that are essential in systems programming, embedded development, or debugging. Here's an example of assembly that we can step through. It adds two values stored in memory, which lines up to our example from an earlier module. In the section.data, we establish some values we want to use in our assembly code, defining two 32-bit integers for 3 and 4, and a result integer for storage of the results. Then we have a section that defines where our program should start, and then the actual contents of our program. The first instruction moves value 1 from memory to register EAX, which is a general-purpose 32-bit register. The second instruction moves value 2 into register EBX. Then we have our add operation that adds the two registers together and stores them in EAX. The order of the arguments matter, as the add operation writes the result from the ALU into the first argument, which is EAX. The last instruction moves the contents of EAX to the memory address held by the result. And that's it. Our assembly program has added two numbers by performing 4 operations. Would you ever write an entire application this way? Probably not. So why bother learning this low-level stuff? because sometimes the only way to fully understand a performance bottleneck or fix a nasty bug is to see what the compiler is doing under the hood. Reading and writing a bit of assembly gives you a window into how your code maps to real instructions and how seemingly minor changes in high-level code can dramatically affect performance. It's not about writing your whole app in assembly, but being able to read it and recognize patterns, and it gives you a serious edge in optimization, debugging, and understanding how your system really works.
Compilers and code optimization.
By now, you're starting to see how much of a role low-level behavior plays in performance. But the truth is, most of us aren't writing in assembly every day or any day. We're writing in C, Go, Rust, or some other high-level language. And it's the compiler that bridges the gap between your code and what the CPU actually runs. So what is a compiler? At its core, it's a translator turning human-readable code into machine instructions.
Okay.
But it's also a performance optimizer, often making your code faster and smaller than you could ever do by hand.
Yeah.
Let's break it down. When you write some C code and compile it, the compiler goes through several steps. First, parsing and analysis.
Okay.
This breaks your code into tokens, building a syntax tree and checking it for correctness. Then, intermediate representation, which turns your code into a form that's easier to analyze and optimize. Then one or more optimization passes where the compiler rewrites your IR to be more efficient. This is where the magic happens. Finally, code generation. The compiler emits assembly or machine code based on your target architecture. Most compilers have different optimization levels. Tools like GCC or Clang have options to increase the optimization level. For instance, in GCC, you can specify -00, -01, or higher. That flag controls how aggressive the compiler gets with its optimization. -00 gives you very readable output that mirrors your source pretty closely, which is great for debugging. -02 or -03 will start to reshape your code in ways that might not even resemble what you originally wrote, but it can give you a big performance boost.
Okay.
It's a trade-off between a few different factors, which is probably starting to sound like a common refrain. Increasing optimization might lead to faster code execution, but you may also end up with machine code that is harder to debug, crashes or behaves oddly, increases the produced binary size, or takes longer to compile. The compiler is also optimizing for your exact architecture, which may make the code less portable. The lesson here is to use optimization carefully and thoroughly test the results to ensure it functions well on the platforms it's destined to run on. The goal of optimization is to limit the number of instructions a CPU has to run and order them in such a way that the pipeline won't encounter stalls. Some of the most popular techniques leveraged are constant folding, which pre-computes constant expressions at compile time, loop unrolling, which expands loop bodies to reduce the overhead of jumps and branches, inlining, which replaces function calls with the actual function.
Constant folding, loop unrolling, inlining. Constant folding, loop unrolling, fold, constant folding, loop unrolling, inlining.
To avoid the call overhead, dead code elimination, which removes code that has no effect on the program's output, and strength reduction, which substitutes expensive operations like multiplication with cheaper equivalents like addition or bit shifts. Let's say you write this simple loop in.
This is a loop, simple C loop. Like, I don't know any of this. Simple C loop include studio H int main, integer main, int sum equals 0. For int I equals 0, I less than 100, I plus plus, sum plus equals 1. Prints the sum of integers from 0 to 99 is okay, return 0.
It starts with a sum equal to 0 and then uses a for loop to increment that sum by 1 each time until it reaches 100. With -0, the compiler will generate fairly standard assembly that follows this loop structure step by step. We can look at the assembly code by running gcc-s loop.c-o loop.a. This is not especially optimized, and it's also not the easiest to read, but I'll point out a couple things about the assembly code. The code has a loop in it. Under .l2, there's a comparison of 99 to the current value of the loop. If it's less than or equal to, the program jumps to .l3 and performs the loop addition. We can directly correlate what we see in our code to what's in the assembly. But what if I run the same command with -03? Now the assembly is shorter and there's no loop. The compiler pre-computed the value of our sum to be 4,950, and so it just uses that. There's no need for a loop, so the program will run faster. But if there was any other logic in the loop, that might be impacted. Understanding how compilers optimize helps you write code that can optimize more effectively. Sometimes writing clever code actually prevents good optimization, while writing clean, straightforward code gives the compiler more room to work with. In short, compilers are your first and most powerful tool for performance optimization. Learn how they think, and you'll be writing faster code without even touching a single line of assembly, which I think is a good thing.
Okay.
Single line of assembly, which I think is a good thing.
Memory and cache optimization techniques.
If you've ever written a program...
So let's ask ChatGPT this first. Listing compiler optimizations. They are techniques that commonly used to make code faster and without changing what it does. Let's break each one clear. Compute values at compile time instead of runtime. Example: integer x equals 5 plus 3. Okay. Becomes, yeah, it's 8. Okay, saves CPU work, so that has constant folding. Happens before the program even runs. Loop unrolling example: for int I plus plus times, okay. Inlining. Replace the function code with the function's actual code. Okay, strength reduction. What? Compiler. Exam style questions very useful for studying this topic. Are we though?
Seems logically perfect, but still runs slow. The problem might not be with your algorithm. It could be with how your code uses memory. In modern systems, memory access patterns have a huge impact on performance, and that's largely thanks to CPU caches. We talked earlier about how fast caches are compared to main memory. Remember how if a cache hit takes 1 second, a cache miss costs over 8 minutes of waiting if you're looking at it proportionally. A cache miss can delay your CPU by hundreds of cycles. So your goal is simple: reduce cache misses wherever possible. Simple to say, but harder to put into practice. One of the most effective strategies is to improve memory locality. There are two types. Spatial locality refers to accessing memory addresses that are close together. Temporal locality refers to accessing the same memory address repeatedly over time. A classic example of spatial locality is how you might access a 2D array. If you iterate row by row, going through this like 1, 2, 3, 4, you get good spatial locality because memory is typically laid out in row major order in C. But if you tried to access by column, like 1, 5, 9, 2, 6, 10, you'll potentially end up with a lot of cache misses, especially with a larger data set, since the cache algorithm is probably loading by the row. Temporal locality can be improved by using the same memory location over and over. In this instance, your variable in C is pointing to a location in memory. Rather than create a new variable, you can store an updated value in the existing variable, one whose memory location is already stored in cache. The write back to memory can happen at a later point when the cache location needs to be flushed for newer data. Then there's prefetching, which is when the CPU predicts which memory locations you'll need next and loads them into cache ahead of time. CPUs do this automatically, but you can help by writing predictable, linear memory access patterns. There are also manual prefetch instructions in some architectures, but most of the time, smart code structure is enough. Next up is data alignment. Modern CPUs prefer data structures to be aligned to specific byte boundaries. Misaligned data can cause multiple memory accesses or even faults on some architectures. Compilers will usually take care of this, but if you're working with packed structs or custom memory allocators, alignment becomes something that you need to actively manage. Lastly, consider how you lay out data in memory. For instance, using an array of structs can hurt performance if you're only accessing one field repeatedly. Instead, converting to a struct of arrays layout can improve cache usage in cases where you're processing fields independently. Consider a situation where you've created an object or a struct that holds information about a person, but your program only cares about everyone's age and height. It is much faster to store the ages and heights in their own array than to load each person object and read those two values. Being smart about the data layout in memory can greatly reduce cache misses, but it also avoids unnecessary cache usage. Think about how each person struct that you read is going to take up cache space, even if you never use the vast majority of that information again. To wrap it up, memory and cache optimization is about being kind to the CPU's memory hierarchy. Write code that walks through memory in order, avoid random access when you can, and think about how your data is laid out. These small tweaks can add up to big performance gains, especially in tight loops or data-heavy applications.
Okay. Real-world performance tuning or techniques, and that's all.
All the theory in the world won't help you if you don't know how to find what's actually slowing your program down. That's where real-world performance tuning comes into use, with data, tools, and experience to track down bottlenecks and make smart, targeted improvements. Let's start with profiling tools. These are your microscope for understanding where your application is spending time, how often functions are called, and where memory or CPU usage spikes. Some popular tools include gprof, a basic but useful profiler for C programs, perf, a powerful Linux profiling tool that ties directly in kernel, Valgrind or Callgrind, which are great for analyzing memory usage and cache performance. Intel vTune, which is advanced profiling specifically for Intel CPUs. Visual Studio Profiler, which is an integrated tool for Windows development. and Instruments for Mac OS that provides detailed profiling on Apple platforms. Profilers can give you call graphs, CPU usage breakdowns, memory allocation patterns, and even cache hit-miss statistics. Armed with this information, you can figure out where the bottlenecks are and then find ways to optimize your application, hardware, or platform to deliver the best performance. So what are the usual suspects when it comes to bottlenecks? There's inefficient loops, which include nested, unnecessary operations or poor memory access patterns. Then there's frequent memory allocations, especially inside performance-critical paths. There's excessive branching, especially when branch prediction struggles. There's
What the? It's not opening. It's not opening. Draw a dog. Okay, I installed this already. Did I install ADK? Okay, extract. Continue. Okay. Integrated is in there, requires space, entire size. Oh my god. Recommend installation. Now install everything with commonly used features. Customize. The fuck? What do I install, guys? I think V2 Profiler is like enough, no? TPC++ compatible. Okay. Install. Okay, we're gonna install it afterwards. Proof, gproof, perf for Linux, Valgrid for what? Trading errors in C, C++ application. In terms runs executables in the virtual machine. Okay. This is was grind. Why I want to take your shit so hard.
Misses, which are caused by scattered memory access or poor data layout. There's unnecessary I/O, like constantly writing to a disk or to the console, and thread contention, which happens in parallel code, including locks and shared resources that can cause slowdowns. One thing to keep in mind when you're trying to optimize your code is that performance isn't everything, and you can encounter diminishing returns on performance while making everyone's life, including yours, a lot harder. Optimizing is a balancing act with trade-offs. Before you optimize your code, be clear about what you're optimizing for and what will deliver the most impact. It's about balancing performance, maintainability, and clarity. The best optimizations are the ones you can measure, justify, and understand, even months down the line. A buddy of mine used to optimize queries for Oracle databases, and the first thing he always started with were the 10 most common queries and the 10 longest running queries. If any of the queries were on both lists, that meant that they were run often and they took forever. Optimizing that one query would deliver an outsized impact to the application. You can do the same thing looking at the most commonly used functions, methods, and libraries in your code and work from there. The basics of CPU architecture have not changed significantly over the last 80 years, and neither has the theory behind writing and optimizing code to run on the von Neumann architecture. Things may have gotten faster, bigger, and more complicated, but the core principles remain the same. I hope this grounding in the foundations of computing architecture help give you a better understanding of your applications and how to improve their performance in the future.
Okay, thank you, my boy. Thank you, my boy. Thank you for the day, guys. This guy's awesome. We learned really good things. We learned a useful tool, like in the end, software improvement program install. You can install it right now. Okay. We're gonna turn it's gonna restart. Unfortunately I have to stop the streaming. That was all for today. You know, a little bit of short stream, like 3 hours, right? We all learned like optimization, like diagnostics too, right? Which help us diagnose our CPU, RAM, GPU, and stuff like that. Okay, there are pref, pro, gproof, and stuff like that as well, right? Yeah. Yep. That's all. I think that you did not wouldn't enjoy this, and I'm gonna think of a way to actually make it enjoyable. Like I wanna only do streaming with labs and stuff like that. Yeah, I wanna only stream labs, like do the study by myself. You know, 1 hour, 2 hour study is gonna be enough, and I'm gonna do labs. But what I don't understand is that how can I do labs when there is no lab? You know, I think that even like we learned this, right? The lab would have been that opening this tool, but maybe sometimes it's not, right? It would have been such okay, open your get started guide, finish. Intune. What was that? Profiler, right? Intel VTune profiler. Let's see. Okay, great. Okay. Sample. Okay. Configure current project sample metrics. Thank you for choosing a VTM profile or run a demo on how to start then the view performance data. Help tour. New project. Okay, project name. PC check. Create project. Local host, remote Linux, arbitrary host. Let's virtual analysis. Okay, okay, launch application and confirm what to analyze. Okay. Select and configure how to perform analysis. Okay. Copy and customize select analysis type. Okay. Run analysis. Okay. Start application with data collection pause. Resume collection where required. Learn more. Okay. Type binary and source directories for post processing. Click to create a command line version of the selected configuration. Okay. Restart help tool. Okay. Attach the process profile system over external target file specified. Oh, we have to specify. But with the defined variables, managed code profiling mode, native mixed managed. Okay, now let's go to Ask ChatGPT. How can I use Intel vTune profiler to check my system's performance? Personalized style mode. vTune is designed to deep personalize usage bottlenecks. Yep. Şimdi methods. CPU hotspots what uses most CPU, threading efficiency, memory. Oh yeah. Installation with okay. Running basic memory and GUI way. Step by open video profile new project use local analyzer set target your program X. Yeah, with like your our program or attached to a running process. Okay, attached to a process. Process name. Advanced. Hotspots. Bad starting point. The show's best CPU time is spent. Equivalent to watch slows me down. Exploration. Run the analysis. Run your program call. Prefer the touch report to read results. Perf mode. What? Actually, guys, I'm actually, I don't know. What's per F mode? Per F mode. Okay, performance monitoring. Performance monitor. Data collector sets. User defined reports. User defined system. Performance monitor. Okay. I don't understand. New action. Data collector set. System diagnosis. System performance. Add. Change ref type. Add what? The fuck? Add what, bitch? View log data. Oh, operating system processor. What's that? Event trace sessions, event log security, everything's running. Startup event trace, user defined, system diagnosis. Spooler logger, what the fuck are these things, man? What the actual hell, man? View log data. Launch application. Maybe we downloads. No, desktop. Like games like what? Where are the games? Where are the games at? New folder. Not in the new folder. Games. It should be here. It should be here, guys. It should be here, but it's not. It should be games. League of Legends. Open. Let's run the product as administrator. Okay, it had to be running. Let's see. C, program files, Google, Chrome, application, Chrome, open. Okay. Okay. Hotspots, algorithms. Elapsed time is a great indicator for tuning efforts. Compare this method point after optimization. It's really holy. This is like the performance of the application, right? Remove, delete. Yes. Yes. Sample metrics. What's that? Matrix X? Expensive submatrix. Poor, okay, ideal. Effective physical core utilization, 100%. 4 out of 4. Logical core utilization, okay, out of 20. Histogram. So our is 15 out of 20. So we are kind of here. It's poor. What the fuck? 40.8. Okay. Performance core, P cores, and efficient cores. Hotspots. Go. What the fuck? Okay, fuck off. Holy shit, guys, we are doing some fucking optimizations. No, not like diagnostics. It's 03HS. Basically, it's the same. Hmm. Are we okay? Pass head count 17. HPC performance characterization, threading, microarchitecture exploration. There is low memory usage of other hardware resources, memory access. The memory bound metric is high. A single fraction of external pipeline slots could be set due to demand memory load in stores. Accelerators, parallelism, microarchitecture algorithms. Cookbook. And this is okay. What's that? Comparing. This is opening. This is what? Haptor, new open class. Okay, now how do we optimize? Down tree. Flame graph. What the? By the way, guys, if anyone knows like all of these, it's like really high level stuff. This is really high level stuff, man. This is really high level stuff, I think so. What the fuck? Who knows this? Who made these, guys? User mode sampling hardware event based something. Bottom up. Matrix X. Kernel, yeah, we are using kernel. Let me ask ChatGPT. Let me ask ChatGPT. Who actually knows all of these? No one person knows all of this. I think with this professional level performance engineering tooling, the people who really understand it fall into a few groups who actually know these are performance engineers. Write all parentheses level or low level code. C, C++. Computer CPU engineers, the people designing CPUs, compilers. HPC, high performance computing people. Reality check. Run hotspots, look at top function, CPU time, person, that's it. You won't tell me anything, brother. Bottom up, color cache, top down, flame graph, platform. It took how much time? Summary 7 point. Yeah. Same. Yes. 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 Holy. What the fuck? Does the actual fuck it these guys? I don't understand everything. I mean, if there's some world that I'm at the level that I understand any of this, just fuck me in the ass, man. Just fuck me in the ass. Take this butthole and fuck it. Take your work process. Yeah, stream your work process. Fuck no, man. They might fire me, man. No, it's not possible. That's not possible. I'm gonna finish now. Wanna play some Wild Drift, brother? Wanna play some Wild Drift, brother? Dude, these are like really high level stuff. I mean, the fuck? What the actual fuck? Does Harvard provide computer science courses for free? Okay. Yes, my friend. Yes, my friend. I'm a dickhead. Okay, I'm a dickhead. Really big dick. I have really big dick. You know this dick. And this is a dick as well. I'm gonna in the ass. Okay. You, only you, brother, only you. Mm-hmm. Right. I'm telling you. I think this goes through platforms like ADX usually requires payment for it, while the hardware software site is free. Okay, free computer science offerings. CSV is Internet Computer Science is a flagship course covering algorithms, data structures, and languages like C, Python, and SQL. Especially in the certificate with Python, web programming, service, and game development. What's that? What's this, guys? Subject programming. Pace, self-pace, 10 20 hours per week, 5 weeks long. Okay, CS56. A broad and robust understanding of computer science programming, how to think algorithms and solve programming problems efficiently. Concepts like abstraction, algorithms, data structures, encapsulation, or I know what encapsulation means. I know. Security software engineering and web development. Familiar with a number of languages, C, Python, okay. And with a vibrant community of like-minded learners from all levels of experience. How to develop and present a final product to your peers. Learn more on EDX. Of course, this is okay. For biology, it is web program with a Python and JavaScript. Okay, CS1S, computer science, programming using Python for research. CS50 is computer science for business. Computer science 50 is introduction to artificial intelligence with Python. Okay. For lawyers. Functions, event values, conditions, loops, and variables. This is for like in programming and programming. Holy shit. Everything's free. Computer science. School duration difficulty, no, introductory. Okay. Lawyers, programming with Python. Education faculty, webinar machine learning for leaders. What's that? Okay. Introduction to cybersecurity. We might need this, guys. For business and databases with SQL, we also need this, I think. 7 weeks long. Introduction to computer science We have this already. Programs from scratch. Okay. The data science building machine learning models. Quantitative methods for biology, data science building machine learning models. 8 weeks, 8 weeks. Available now. Opens April 15. Okay. How is it self-paced if, okay. Pays self-paced to 6 hours per week, 5 weeks long. Science English is tertiary DX. So there's how to organize level tomorrows as well, both at home as well, then to view series in hotels spots left. For technical and non-technical audiences alike. Providing students with all they need to know technically to understand both assignments or the events. Lemo. International database via SQL. Create table, select, insert, update, delete, drop. I know. I think I know this, no? 7 weeks long. Building machine learning models. What's that? It's the basis of machine learning. Cross-validation for overtraining for the machine learning algorithms. The recommendation system with what is regularization and why it is useful. Hey. Overtraining. Skip. 9 weeks long. 1 week long. Free is a variant. Subject area: computer science, programming, science, social science, mathematics, health, mathematics, data science. Do we have anything for Linux? Air basics. Set. I know how to start the repo. I already know how to start the repository on GitHub. How to perform a version control with Git. Okay. Don't want that. Yes, it is an introduction program with Scratch. 3 weeks long, self-paced, computer science, English. Do we have it opened already? What's that? Computer science. Okay, we have already opened that. Science, program with Scratch. We have science, programming, cybersecurity, which I think that we don't need. So, next course starts April 01. What's that? This is ADX now. Program review, overview. This is like certificate. 2 courses. Okay. So basically, this one was free. How can I? How? Deeper learning experience. What the? Okay, for example, register for free, right? We can register name, email. We can register both with this. Okay, let's go. Continue. Okay. I have almost completed my bachelor's degree, guys, so chill out. So we can skip it for now, actually. I don't want to indicate. Oh, we have to edit on our dashboard. This is, how do we know the edit now? don't want to. What's that? Computer Science 101. What's that? You learn? Dude. Oh my god. ADX courses, computer science. Computer science and cybersecurity, 2 courses, 5 months to introduction level. Dude, guys, help! I need help. I don't know what to do. They have lost me. There's so much courses in here. What the fuck is this? Business level availability. Simply translation language. Level introductory. Course language. English. Learning type. Educator. IBM, Google Cloud, Microsoft, and Linux Foundation. Where's the Maryland? Is it Maryland? Information Technology. Resource Management. Okay, Maryland. There is no Maryland. Okay. Okay, learning type was the level. Okay. Clear all. Learn. Okay, there is this CS50's Introduction to Computer Science. How to learn the science of happiness, remote workflow. Okay, education courses. Fucking hell, man. Fucking hell, man. Audit course. What does it mean? Audit course. Begin your course days. Okay. Okay. Scratch, C, Arise, Memory, Data, Python, SQL, let's change to the end. Wholeness at 0. What's that? What? fuck? Fuck this shit. Fuck this shit. Holy. What was on our? Let me first finish this. We're gonna see what I will be doing next. But no. What? Okay. $18, $15, $13, half an hour. Okay. This is like not bad. I don't know. We'll see. We'll see. We'll see. We'll see, guys. Let's end it for now.